Imagine you are standing on a ship, a vessel the size of a small city, drifting silently through the absolute darkness between the stars. This is the dream of the generation ship. So why do the scientists who study it seriously come away convinced we would never survive? If you love exploring the big questions of the cosmos, please subscribe to the channel. Now let's get started. Our fastest spacecraft ever launched, the Voyager 1 probe, which has been flying through space since 1977, travels at roughly 61,000 kilometers per hour. At that speed, it would take Voyager 1 approximately 73,000 years to reach Proxima Centauri. That is longer than modern human civilization has existed, longer than the oldest known cave paintings, an almost incomprehensible stretch of time. But for a generation ship, a vessel built not for raw speed, but for sustained survival across a multi-century journey, the numbers that get thrown around in serious scientific literature range from roughly 300 years on the very optimistic end, assuming propulsion technologies we do not yet fully possess, all the way up to several thousand years using more realistic near-future concepts. Let us be generous. Let us say 300 years. Think about what the world looked like 300 years ago. It was 1725. There were no computers, no antibiotics, no understanding of DNA. The steam engine had not yet been invented. Most human beings never traveled more than a few dozen kilometers from where they were born. The entire framework of what it means to be human, socially, medically, psychologically, was fundamentally different from anything we know today. Now imagine sealing a group of people inside a metal structure and telling them, your great-great-great-great-grandchildren will be the ones who finally arrive at the destination. You will never see it. Your children will never see it. Their children will never see it. Generation after generation, born inside the same enclosed space, living their entire lives there, and dying there, never knowing anything else. This is not science fiction anymore. This is a serious scientific and philosophical challenge, and researchers around the world have spent decades examining whether it is even remotely survivable in the way we imagine. The emerging answer, based on everything we currently know, is deeply troubling. So let us start with the very first massive obstacle, one that begins the instant the ship clears Earth's orbit: radiation. Space is trying to kill you. That sounds dramatic, but it is the honest scientific truth. The moment you leave the protective embrace of Earth's magnetic field, what we call the magnetosphere, you are exposed to one of the most hostile radiation environments imaginable. On a journey lasting centuries, that exposure is not just a health risk. It is a potential extinction-level event for the crew, unfolding slowly and invisibly across generations. Here is what you are actually up against. There are two primary sources of deep space radiation that concern scientists most. The first is solar energetic particles, often abbreviated as SEEBs. These are high-energy particles blasted outward by our Sun during solar flares and coronal mass ejections, in enormous explosions on the Sun's surface that send waves of charged particles tearing through space at extraordinary velocities. On Earth, we barely feel these events. Our magnetosphere deflects the vast majority, and our atmosphere absorbs what gets through. But on a generation ship drifting through interstellar space, those particles would punch straight through insufficient shielding and directly into biological tissue. The second source, and in many ways the more terrifying one, is galactic cosmic rays, or GCRs. These are not particles from our own Sun. These are high-energy atomic nuclei, often the cores of atoms, stripped entirely of their electrons, accelerated to near-light speed by violent cosmic events like supernova explosions and the relativistic jets produced by black holes. They arrive from every direction, from all across the Milky Way and even from distant galaxies, streaming continuously through space in every direction, all the time, and they are extraordinarily difficult to stop. NASA has been studying cosmic ray exposure extensively through the International Space Station program. Astronauts aboard the ISS receive roughly 100 times more radiation than people on Earth's surface, and the station still benefits from partial protection because of its relatively low orbital altitude within Earth's magnetic field. In deep space, beyond that protection entirely, the doses would be substantially higher. A crewed mission to Mars and back, estimated at roughly 2 to 3 years, would expose astronauts to radiation doses approaching or exceeding the career exposure limits that NASA sets for its astronaut corps. Now multiply that journey not by 1, but by 100, or 300, or 1,000. The long-term biological consequences of chronic high-dose radiation are well documented and severe. We are talking about dramatically elevated cancer risk, particularly leukemia and solid tumors in multiple organ systems, damage to the central nervous system, measurable cognitive decline, accelerated development of cataracts, cardiovascular disease, and deeply compromised immune function. Research on survivors of the Chernobyl disaster and long-term studies of cancer radiotherapy patients give us sobering real-world data on what sustained radiation exposure does to the human body across years and decades. But the generation ship problem cuts even deeper than individual health outcomes. Radiation damages DNA. When it damages the genetic material inside reproductive cells, the eggs and sperm that will create the next generation, it introduces mutations that get passed forward. Over many generations of continuous exposure, you could be looking at an accumulating genetic burden spreading through the ship's entire population, rising rates of heritable mutations, increasing frequencies of genetic disease, a slow, invisible erosion of the population's collective biological health, compounding across centuries. Shielding is the intuitive solution, and engineers have spent years designing around it. Water, remarkably, is a decent radiation absorber, and some serious proposals call for lining the outer hull with thick tanks of it. Polyethylene, a hydrogen-rich plastic, has also been seriously studied. But here is the brutal constraint at the heart of every proposal. The more shielding material you add, the heavier the ship becomes. And the heavier the ship, the more propulsion energy you need to accelerate it to any meaningful fraction of the speed of light. And the more energy you need, the more fuel mass you carry, which makes the ship heavier still. Engineers refer to this as the tyranny of the rocket equation, and it is one of the fundamental physical barriers standing between us and the stars. Some of the more ambitious concepts propose using the ship's own structural layout as passive shielding, positioning water tanks and fuel reserves around the inhabited sections of the vessel. Others have suggested active magnetic shielding, generating an artificial magnetosphere around the ship using powerful superconducting magnets, mimicking the protection that Earth's own magnetic field provides. The physics suggests this is theoretically possible. The engineering reality is that no one has come close to building anything of the kind, and the power requirements alone are staggering. The bottom line on radiation is stark and honest. After decades of serious scientific inquiry, we do not yet have a fully verified, practically buildable solution to shielding a crew from galactic cosmic rays across a journey measured in centuries. It remains one of the most unresolved and consequential problems in the entire field of interstellar mission planning, and that is only the first problem on a very long list. So now you understand the radiation problem. You understand that the moment a generation ship leaves the protective cocoon of Earth's magnetic field, every living soul aboard is swimming in an ocean of invisible, high-energy particles that will work on their bodies and their DNA for the entirety of the journey, and we have not yet solved that problem in any complete, practical, buildable way. But let us say, for the sake of argument, that we crack it. Let us say brilliant engineers develop a shielding solution that genuinely works, that keeps the radiation exposure low enough across centuries that the population remains biologically healthy. Remarkable, extraordinary, a triumph of human ingenuity. You still have to keep everyone alive, and that means you have to feed them, give them clean water to drink, give them air to breathe, manage their waste, maintain stable temperatures, cycle nutrients through a closed biological system indefinitely with no resupply, no emergency deliveries, no possibility of stepping outside to gather resources. This is the closed ecological life support problem, and it is arguably even harder than the radiation challenge because unlike radiation, which is a physics problem with theoretical engineering solutions, this is a biology problem, and biology is messy, unpredictable, stubborn and deeply resistant to being engineered into perfect, permanent stability. Let us talk about what a closed life support system actually has to do. On Earth, you breathe in oxygen and exhale carbon dioxide. Plants absorb that carbon dioxide, use sunlight to drive photosynthesis, produce oxygen, grow organic matter, and eventually become food. Decomposers, bacteria, fungi, worms, an enormous web of microscopic life break down dead organic material, recycling its nutrients back into soil that grows more plants. Water evaporates, forms clouds, rains down, filters through soil, flows through rivers, and eventually returns to the ocean. Everything connects, everything cycles. The entire system is self-correcting and self-sustaining across geological timescales. Your generation ship needs to replicate all of that inside a metal tube for centuries. This is not a new idea. NASA and other space agencies have been studying closed ecological systems since the 1960s. The Soviet space program ran a remarkable series of experiments in the 1970s and 80s called BIOS-3, sealing small groups of researchers inside a closed facility in Siberia and attempting to sustain them primarily through indoor farming with minimal outside inputs. The results were illuminating and cautionary. The system worked after a fashion, but it required constant human intervention to stay balanced. Oxygen levels drifted. Certain crops failed unexpectedly. The system never achieved anything close to full closure, meaning some inputs and outputs still had to cross the boundary between inside and outside to keep things stable. Then there was Biosphere 2, built in the Arizona desert and launched as a bold experiment in 1991. 8 researchers, called biospherians, were sealed inside a massive, airtight glass and steel structure covering roughly 1.27 hectares, containing a rainforest, an ocean, a savanna, a mangrove wetland, agricultural land, and a human habitat. The goal was full ecological closure for 2 years. It did not go as planned. Oxygen levels dropped unexpectedly and dramatically. The culprit turned out to be soil microbes consuming oxygen at rates the designers had not anticipated. The team had to pump oxygen in from outside to prevent the crew from suffering altitude sickness symptoms. Carbon dioxide levels swung wildly. 19 of the 25 vertebrate species inside the structure went extinct during the mission. Populations of ants and cockroaches exploded uncontrollably. Morning glory vines spread so aggressively they began choking out food crops. Food production fell short, and the crew lost significant body weight, operating on a restricted calorie intake for much of the 2 years. And Biosphere 2 had advantages a generation ship never would. It sat on Earth. Sunlight poured through its glass panels from the actual sun. Outside scientists monitored and adjusted. When oxygen dropped dangerously, they could, and did, intervene. A generation ship in interstellar space has none of those safety nets. It is completely, absolutely isolated. The nearest source of help is growing more distant every single second. Now let us think about scale. A generation ship capable of sustaining a viable human population across a multi-century journey would likely need to carry somewhere between 10,000 and 40,000 people. Based on the population genetics research we will discuss a little later in this video, supporting that many people requires enormous quantities of food, water, and oxygen continuously, without interruption, without collapse, for 300 years or more. The caloric requirements alone are staggering. An average adult human needs roughly 2,000 kilocalories per day. At 10,000 people, that is 20 million kilocalories every single day. The agricultural systems required to generate that output would need to be extraordinarily efficient, far beyond anything we currently operate, and they would need to run flawlessly for generations. Modern industrial agriculture on Earth uses enormous external inputs: fossil fuel-derived fertilizers, pesticides synthesized from petrochemicals, diesel-powered machinery, and an open hydrological cycle that continuously replenishes fresh water. None of that is available on a generation ship. The entire nutrient cycle has to be closed. Every kilogram of nitrogen, phosphorus, potassium, and trace mineral that goes into a plant has to come back out of the system through composting, through waste processing, through the biological breakdown of dead organic matter, and go back into the growing medium. Lose any significant fraction of that nutrient budget, and crop yields decline. Let yields decline long enough, and people begin to starve. Water presents its own extraordinary challenge. A human being needs about 2 liters of drinking water per day at minimum, plus water for cooking, hygiene, and agriculture. Total water usage per person in a reasonably comfortable living environment runs to dozens of liters daily. Across tens of thousands of people, across hundreds of years, the total water throughput is astronomical, and every single molecule of it must be recaptured, purified, and recirculated within the closed system. Advanced water reclamation technology exists. Aboard the International Space Station, urine and condensed atmospheric moisture are processed back into potable water with remarkable efficiency. But the ISS is a tiny installation with a crew of 6 or 7, and it is resupplied regularly. Scaling that technology to a city-sized vessel and operating it without resupply for 3 centuries is an engineering challenge in an entirely different category. And then there is the atmosphere itself. Maintaining breathable air inside a closed system is not simply a matter of having enough plants. You need to balance oxygen and carbon dioxide levels precisely. You need to manage humidity, which affects both human comfort and the rate of microbial growth on surfaces. You need to handle trace contaminants, off-gassing from materials used in construction, metabolic byproducts from the humans and animals aboard, volatile organic compounds produced by decomposing organic matter. On the International Space Station, atmospheric management is handled through a sophisticated combination of chemical scrubbers, electrolytic oxygen generators, and carbon dioxide removal systems, all of which require regular maintenance and periodic replacement of components. Over 300 years, every single one of those systems would need to be maintained, repaired, and eventually replaced entirely, multiple times over, using only the materials and manufacturing capacity already aboard the ship. This points to one of the deepest structural problems with the generation ship concept. It is not just a vehicle, it is an entire civilization compressed into a finite volume with a finite material budget, expected to sustain itself in isolation for a time frame that dwarfs the entire history of recorded human civilization. Consider what happens when a critical system fails. On Earth, if a water treatment plant breaks down, engineers can order replacement parts. Specialists can fly in from anywhere in the world. If the worst happens, alternative sources of water can be found. On a generation ship 4 light weeks into its journey, there is no calling for help, no ordering of parts, no alternative. Every critical system, life support, water reclamation, food production, power generation, structural integrity, must either be repairable using resources already aboard, or it must be redundant enough that its failure does not cascade into catastrophe. Redundancy is critical but brutally expensive in mass and space. Every backup system adds weight. Every kilogram of weight requires more energy to accelerate, and energy in deep space is another finite, precious resource with no external replenishment. But if you are sitting there thinking, what if we built something dramatically faster? What would the numbers actually look like? I have a full video on exactly that on the card above, and I cannot recommend it enough as a companion to what we are exploring today. It connects directly to everything we are about to discuss. The link is pinned on the comments. Some researchers have proposed that the solution lies in extreme automation and artificial intelligence. Systems smart and adaptive enough to monitor, diagnose, and repair the ship's ecology without constant human oversight. That is a genuinely interesting idea, and it is worth taking seriously. But we have never built autonomous systems that reliably operate correctly and safely across timescales of centuries. Software accumulates errors, hardware degrades. Even the most robust artificial intelligence systems we can currently imagine were designed, programmed, and trained by humans, and will reflect the knowledge, assumptions, and blind spots of the era in which they were created. Trusting a civilization's survival to software written 300 years ago, in a context its designers could not have fully anticipated, is an extraordinary gamble. Here is the core truth of the ecological life support problem. Every closed biological system we have ever built has eventually failed, or required external intervention to prevent failure. We have never once in all of recorded history maintained a fully closed, fully self-sustaining biosphere at any scale for any extended period. Not for a decade, not for a century, certainly not for 3 centuries. That does not mean it is impossible. It may be achievable with technologies and understanding that we have not yet developed. But the honest scientific assessment, based on everything we currently know, is that we are nowhere near ready to build a closed life support system robust enough to sustain tens of thousands of people across centuries without failure. And the third problem, which we will begin exploring in part 3, may be the strangest and most deeply human challenge of all. So far, you have seen 2 enormous obstacles standing between humanity and a successful generation ship mission: radiation that silently damages DNA across centuries, and a closed ecological system that we have never, not once, managed to keep stable for anything approaching the timescales we are talking about. Both of those problems live in the realm of physics and engineering. They are hard. They may be solvable, given enough time and enough brilliant minds working on them. But the problem we are about to explore is different. It lives in the realm of biology, specifically genetics, and it operates according to mathematical rules that do not bend, do not negotiate, and do not care how advanced your technology is. It is quiet, invisible, and absolutely relentless. And if you get it wrong at the very beginning, before the ship ever leaves Earth's orbit, there may be no recovering from it. No matter what you do later, it is the population genetics problem. And it comes down to one deceptively simple question: how many people do you actually need? Let us start with a concept that geneticists call the minimum viable population, or MVP. This is the smallest number of individuals of a given species needed to maintain long-term genetic health, meaning enough genetic diversity that inbreeding does not progressively weaken the population across generations, and enough individuals that random chance events cannot wipe out critical genetic variants entirely. For most large mammals, the numbers that come out of population viability analyses are sobering. You are generally looking at several hundred individuals, at the absolute minimum, to avoid what biologists call inbreeding depression, the accumulation of harmful recessive genetic mutations that show up when closely related individuals reproduce together. But several hundred is the emergency floor, not a comfortable operating number. At that level, you are perpetually teetering on the edge. For a multi-century journey, you need to think far beyond the minimum. You are not just trying to survive, you are trying to arrive with a population that is still biologically healthy enough to colonize a new world. That requires a completely different calculation. In 2013, a researcher named Cameron Smith at Portland State University published a study in the journal Acta Astronautica that became one of the most cited papers in the field of interstellar mission planning. Smith ran detailed population genetics simulations for a hypothetical generation ship mission lasting 300 years, roughly the duration of a journey to Proxima Centauri using propulsion technologies that might be achievable within the next century or two. His conclusion was striking: to maintain sufficient genetic diversity across 300 years, accounting for natural mortality, generational turnover, and the statistical realities of random genetic drift, you would need a founding population of at least 10,000 people. 10,000, not 100, not 500, not even 1,000. 10,000 human beings, sealed aboard a vessel for 3 centuries, just to preserve the genetic health of the population by the time it reaches its destination. And even 10,000 is not a comfortable number. It is a working minimum. Smith's models showed that with 10,000 founders, the mission could survive a catastrophic mortality event, a disease outbreak, an accident, a structural failure that killed up to 30% of the population and still retain enough genetic diversity to continue. Below 10,000, that buffer essentially disappears. A single bad generation, one epidemic, one systems failure, one particularly harsh period of resource scarcity, and the genetic bottleneck becomes irreversible. To understand why, you need to understand 2 key mechanisms that geneticists worry about in small, isolated populations. The first is genetic drift. In a large population, the genetic frequencies of any given variant, any particular version of a gene, stay relatively stable over generations because the law of large numbers smooths out random fluctuations. But in a small population, random chance plays a much bigger role. Some individuals happen to have more children than others, not because of any genetic advantage, but simply by luck. Some genetic variants happen to be carried by people who die young, not because those variants are harmful, but simply by misfortune. Over generations, this randomness causes some genetic variants to become more common and others to disappear entirely, a process called fixation and loss. The smaller the population, the faster this happens, and once a genetic variant is lost from the population, it is gone forever. That lost diversity can never be recovered. The second mechanism is what happens when you combine reduced genetic diversity with reproductive patterns inside a small, isolated community. As the generations pass and the gene pool narrows, the probability that any 2 individuals who choose to reproduce together share copies of the same recessive mutations inherited from common ancestors increases steadily. When 2 copies of the same harmful recessive mutation meet in a single individual, that individual expresses the mutation. This is inbreeding depression, rising frequencies of genetic disease, reduced fertility, compromised immune function, lower birth weight, higher infant mortality. It is not dramatic or sudden. It creeps in gradually, generation by generation, like water quietly wearing down stone. We have watched this process play out in isolated animal populations with devastating clarity. The Florida panther, by the 1990s, had been reduced to roughly 20 to 25 individuals in the wild. The population showed severe inbreeding depression, kinked tails, heart defects, poor sperm quality, high rates of infectious disease. Wildlife managers eventually introduced 8 female panthers from a genetically distinct Texas population, and the influx of new genetic material reversed many of the problems within just a few generations. The population recovered. On a generation ship, there is no Texas population to draw from. There are no fresh genetic lines available anywhere in the universe except the ones you sealed inside the hull when you left. Now here is where the problem becomes even more psychologically complex. Maintaining genetic diversity across 300 years is not simply a matter of having 10,000 people aboard at the start. You also have to manage how those people reproduce across generations. You cannot just let people pair off naturally and hope the genetics work out. To maintain diversity, you need to ensure that genetic variants are distributed across the population in a healthy way, that no particular lineage becomes dominant, that no particular subset of the population becomes the genetic ancestors of everyone aboard by the time you arrive. Some researchers have proposed genetic management programs, essentially using detailed genomic databases to guide reproductive decisions, ensuring that individuals with rare or valuable genetic variants are encouraged to reproduce, and that the overall distribution of genetic diversity remains healthy across generations. In practice, this means telling people who they should and should not have children with based on their genome profile. Take a moment to sit with that idea. Take a genuine moment with it. You are asking people, real human beings, with their own desires and emotions and deeply personal relationships, to subordinate some of the most intimate decisions of their lives to the requirements of a population genetics spreadsheet. You are asking them to accept, as a matter of civilizational survival, that their reproductive choices are not entirely their own. How many people would agree to that willingly? How many would resist? How would that resistance be handled? What happens in Generation 3 or Generation 7 when the original mission founders are long dead and the only people alive have never known anything except the ship, and the genetic management program feels not like a rational precaution but like an oppressive system imposed on them by people who have been dead for 100 years? We will come back to those questions in devastating detail when we get to the psychology and sociology of the mission. But for now, hold on to that thread, because it ties directly into the next dimension of the population genetics problem, one that most people never think about. It is not just about genetic diversity, it is about skills. A generation ship is a closed civilization. Every skill, every area of knowledge, every technical discipline that the ship requires to function must be present aboard, not just at departure, but at every point during the journey, including centuries in. And skills are not inherited genetically. They are learned. They are transmitted culturally from one generation to the next through education and apprenticeship and practice. Think about all the specialized knowledge required to operate a vessel of that complexity. You need engineers capable of maintaining the propulsion system, the life support systems, the power generation infrastructure, the structural integrity of the hull. You need physicians capable of performing surgery, managing chronic disease, handling psychiatric emergencies. You need geneticists to manage the population genetics program. You need agronomists to manage the food production systems. You need computer scientists, chemists, materials scientists, educators, psychologists, administrators. In a population of 10,000, spread across a multi-century mission, any particular specialization might be represented by only a handful of individuals at any given time. If the one person aboard who fully understands how to repair the primary water reclamation system dies unexpectedly before fully transmitting that knowledge to an apprentice, the knowledge is gone. Not temporarily unavailable, gone. and the consequences of that absence might not become apparent until years later when the system begins to fail and no one alive knows how to fix it. Researchers have studied what they call knowledge extinction in small, isolated communities, and the pattern is consistent and concerning. Critical technical knowledge can be lost within a single generation if institutional structures for transmitting it break down, and institutional structures are fragile things. They depend on continuity, on social stability, on people choosing to participate in them. None of those conditions are guaranteed across centuries aboard a ship, where the mission's original purpose may itself have become contested or forgotten. Some proposals suggest comprehensive digital documentation, storing the complete technical knowledge base of the ship in redundant computer systems accessible to anyone who needs it. That is a sensible precaution, but it raises its own questions. Can you maintain those systems across 3 centuries? Can you ensure that the people who find themselves needing the information in Generation 15 have the foundational education to actually understand and apply it? Technical knowledge is not just a collection of facts. It is a set of deeply contextual skills built up over years of training and practice. Reading a manual is not the same as knowing how to do the thing. The population genetics problem, in its full dimensionality, is not just a biology challenge, it is a civilizational architecture challenge. You are trying to design a society, its size, its reproductive patterns, its educational institutions, its cultural transmission mechanisms, that will remain functional and coherent for 3 centuries in total isolation under conditions of extraordinary stress. And you have to get it right before you leave, because once you are gone, there is no course correction available from outside. The honest scientific assessment is that we have no model for how to do this successfully. We have population genetics models. We have studies of isolated communities and island populations and small-scale societies. We have cautionary tales from every corner of biology about what happens when gene pools narrow and skills atrophy and institutional knowledge disappears. What we do not have is a single example of a self-contained human civilization maintaining biological and technical health across 300 years of complete isolation. Not one. And the biology and the genetics, as daunting as they are still not the deepest layer of the problem, because all of that assumes the people aboard remain psychologically functional across the centuries. It assumes they remain willing to maintain the ship, committed to the mission, cooperative with each other, and mentally healthy enough to raise the next generation with the stability and competence required. And that assumption may be the most fragile assumption of all. If you are enjoying this journey, make sure to subscribe to the channel and give this video a like. Every video we put out is designed to expand the way you see the universe. Let's keep exploring together. There is a research facility on the edge of the Antarctic plateau, sitting at an altitude of roughly 3,200 meters above sea level, where the average winter temperature drops to around -60 degrees Celsius and the sun disappears entirely for months at a time. It is called Concordia Station, and it is operated jointly by the French and Italian Antarctic programs. During the winter over period, a small team of researchers, typically between 13 and 16 people, are completely isolated there for roughly 9 months. No flights in, no flights out. The nearest human beings are hundreds of kilometers away, across one of the most hostile landscapes on Earth. The European Space Agency has been using Cordia as a psychological research laboratory for years, specifically because the conditions, the isolation, the confinement, the monotony, the darkness, the small group dynamics approximate certain aspects of a long-duration spaceflight better than almost any other environment on Earth. What the researchers have found there is fascinating, deeply human, and quietly terrifying in the context of what we are discussing today. Let us start with something called psychological wintering over syndrome, or more informally, the third quarter phenomenon. In virtually every documented case of extreme long-duration isolation, Antarctic winter over missions, submarine deployments, early polar expeditions, researchers observe a predictable pattern in crew psychological health over time. The first phase is characterized by excitement and high motivation. Everything is new. The mission feels meaningful and urgent. People are engaged, cooperative and energized. Then comes the long middle. The novelty wears off completely. The environment stops changing. The same faces appear at every meal, in every corridor, at every meeting. The same conversations repeat. The same irritating habits of the same people grate in the same ways every single day. Motivation drops. Mood deteriorates. Sleep patterns often become disrupted. Cognitive performance on certain tasks measurably declines. A kind of psychological flatness sets in. Researchers describe it as a loss of the sense that time is passing meaningfully, a feeling of being suspended in an endless, featureless present. The third quarter phenomenon refers specifically to the observation that psychological distress tends to peak not at the halfway point of the mission, but roughly 3/4 of the way through. The end is close enough to feel real, but still far enough away that the exhaustion and frustration of confinement becomes almost unbearable. Interpersonal conflicts intensify. Minor irritations escalate into serious disputes. The social fabric of the small group strains under the accumulated weight of months of enforced proximity, and that is for missions measured in months, with teams of fewer than 20 people who all volunteered knowing exactly what they were getting into, who have regular communication with their families and the outside world, and who know with absolute certainty that they will go home. Now scale that up by every dimension simultaneously. A generation ship carries not 20 people, but potentially tens of thousands. The mission lasts not 9 months, but 300 years. Most of the people aboard did not volunteer. They were born there, and they will die there, and they never had any choice about any of it. Communication with Earth becomes increasingly meaningless as the ship travels further. At 1 light-year of distance, a message sent home takes 1 year to arrive and another year to receive a response. By the midpoint of the journey, Earth is effectively as unreachable emotionally as it is physically, and there is no going home, not ever, not for anyone alive. The psychological implications of that reality are staggering, and they operate on multiple levels simultaneously. Start with the most fundamental, the absence of choice. Every framework of modern psychological understanding emphasizes autonomy, the sense that you have meaningful control over the direction of your own life, as one of the most critical determinants of human well-being. Research in self-determination theory, developed by Edward Deckey and Richard Ryan over decades of empirical work, consistently identifies autonomy as one of 3 basic psychological needs whose satisfaction is essential for healthy motivation, mental health, and flourishing. The other 2 are competence, the feeling that you are effective at meaningful things, and relatedness, genuine connection with other people. Now consider the situation of someone born on a generation ship in, say, Generation 5. They did not choose to be there, they cannot leave. The entire arc of their life, where they will live, what work they will do, how many children they can have, and with whom, is substantially determined by the requirements of the mission and the constraints of the ship's systems. Their autonomy is radically curtailed compared to anything human beings have experienced in any society in recorded history, even the most restrictive ones, because even in the most restrictive societies, people could theoretically run away, or imagine running away, or conceive of a world beyond the walls. On a generation ship between the stars, there is no beyond, there is only the ship. in every direction, for distances that dwarf comprehension, there is nothing. What does that do to the human psyche across generations? We genuinely do not know. We have never done this to people before. But we have studied communities that approximate elements of it, and the findings are not encouraging. Research on multi-generational island communities, isolated religious communities, long-duration prison populations, and historical cases of groups cut off from the broader world, such as the Pitcairn Island community, settled by the Bounty mutineers and their Tahitian companions in 1790, which spent decades in total isolation, consistently shows the same patterns, intensifying social stratification, the emergence of rigid hierarchies, interpersonal conflicts that escalate into violence, the development of closed ideological systems resistant to outside challenge, and the concentration of power in the hands of small groups who use it to control others. The Pitcairn community, despite numbering only a few dozen people, descended into a cycle of violence, abuse, and trauma within a few generations that persisted for over a century. And Pitcairn had something a generation ship would not: the actual physical world outside, the ocean, the sky, the horizon, natural cycles of light and darkness and weather and season that ground human experience in something larger than the social group. Inside a generation ship, even those anchors are artificial. Light comes from lamps running on the ship's power systems. Seasons, if they exist at all, are simulated. The sky is a wall, the horizon is a corridor. Every sensory experience that has shaped human psychology across hundreds of thousands of years of evolution, open landscapes, natural light, the sounds and smells of a living biosphere, the experience of weather, the visual infinity of the night sky, is absent, replaced by a carefully managed artificial environment. Now let us talk about something that does not get discussed nearly enough in generation ship conversations: mission drift. This is perhaps the most profound long-term psychological and sociological challenge of all, and it emerges not from any individual's dysfunction, but from the completely natural and deeply human tendency of each generation to make meaning of their own lives on their own terms. The founders of the mission, the people who chose to leave Earth, who understood why, who felt the weight and the glory of what they were attempting, are dead within the first generation or two. Their children grew up hearing about the mission, understanding it intellectually, perhaps feeling some inherited sense of its importance. Their grandchildren are further removed. By generation 5 or 6 or 10, the Earth these people theoretically left is not a memory. It is not even a story passed down by people who remember. It is a myth, an abstraction, a place described in old documents and video recordings featuring people who look faintly like them but whose world is entirely foreign. Why should those people care about arriving at Proxima Centauri b? What does that destination mean to someone who has never known any other home but the ship? The ship is their world. The ship is everything they have ever known. The mission, this vast, transgenerational project conceived by people long dead, is something imposed on them from outside history. And human beings, psychologically, do not sustain meaningful commitment to abstract goals imposed on them by dead ancestors across centuries of hardship and sacrifice. Historians and anthropologists have studied the decay of institutional purpose in long-lived organizations extensively. Even well-funded, highly motivated, purpose-driven institutions, religions, political movements, corporations, scientific projects tend to experience significant mission drift within decades, let alone centuries. Goals get reinterpreted, original intentions get distorted. New leadership brings new priorities. The original vision becomes a relic, recited in ritual form, while the actual lived culture of the organization moves in entirely different directions. On a generation ship, mission drift is not just an organizational problem, it is an existential one. If the population in Generation 12 decides collectively that the mission is illegitimate, that they never agreed to travel to some distant star, that they want to turn the ship around, that they want to reorganize their society in ways incompatible with the original mission parameters, what happens then? Who has the authority to stop them? Some theorists have proposed rigid governance structures, constitutional frameworks written at departure that legally bind all future generations to the mission's requirements. But constitutional frameworks only work when the people subject to them accept their legitimacy. Throughout history, every attempt to bind future generations to the decisions of their ancestors has eventually broken down when those future generations decided it no longer served their interests. The American Constitution has been amended 27 times. Magna Carta was reissued and revised repeatedly. Constitutions get overthrown in revolutions. Laws get repealed. Social contracts get renegotiated. On a generation ship, a revolution does not just change the political order. It could end the mission entirely. It could redirect the ship's resources. It could dismantle the systems that keep everyone alive if the conflict becomes violent enough. And violence brings us to another dimension of the psychology problem that deserves serious attention. Conflict and crime in a closed society with no exit. On Earth, human societies manage conflict through a combination of legal systems, physical separation, and the ultimate option of exit, the ability for individuals or groups to leave a community when tensions become irreconcilable. Divorce, emigration, moving to a different city or country, starting a new community elsewhere. The entire history of human civilization is in part a history of people moving away from places and situations they cannot tolerate. On a generation ship, exit is impossible. Every person who becomes a threat to social cohesion, every individual whose behavior puts the community at risk, every unresolvable conflict between factions, all of it must be managed entirely within the closed system. Incarceration consumes resources and requires infrastructure. Execution, killing people to protect the community, is both morally catastrophic and genetically damaging in a small population where every individual's genetic contribution matters. Exile is literally impossible. Research on long-duration isolated groups consistently shows that interpersonal conflict is the single most commonly cited source of psychological distress, far outpacing the physical challenges of the environment. On the International Space Station, careful crew selection and psychological support protocols are maintained precisely because interpersonal conflict in a small, isolated crew is mission-critical. NASA spends enormous resources screening astronaut candidates for psychological resilience and compatibility, specifically because they know what happens when it goes wrong. Screening 10,000 people for psychological compatibility and then managing the social dynamics of their descendants across 300 years is a challenge of an entirely different order of magnitude. Here is what makes all of this not just frightening, but genuinely profound. Every single one of these psychological challenges, the need for autonomy, the hunger for meaning, the tendency toward conflict, the resistance to being bound by the decisions of the dead, is not a flaw. It is not a bug in human psychology that better engineering could eliminate. These are features. These are the characteristics that have made human beings the most adaptable, creative, and resilient species this planet has ever produced. Our stubbornness in the face of authority, our insistence on making our own meaning, our refusal to simply accept the world as we found it, these are the qualities that produced science, that produced art, that produced philosophy and music, and every act of rebellion that ever pushed the human story forward. And they are precisely the qualities that make a 300-year, multi-generational mission in a closed metal tube profoundly, perhaps fundamentally, incompatible with the kind of human beings we actually are, which raises a question so large it almost defies articulation. If we cannot change the physics, and we cannot change the biology, and we cannot change the psychology, can we change ourselves? Is there a version of this mission that works, not by solving the human problem from the outside, but by reconsidering what it means to be human in the context of the cosmos? That thread, the most philosophical and perhaps the most important one, we will pick up later in this series. But first, we are going to look at something that sounds almost mundane compared to everything we have discussed so far, but which represents one of the most technically underappreciated catastrophic risks of the entire mission: mechanical failure across centuries. What happens when the machines that keep everyone alive start to break down, and no one alive knows how to fix them? There is a clock ticking inside every machine ever built by human hands. You cannot hear it, you cannot see it, but it is there, counting down with absolute mathematical certainty toward the moment when something fails. A bearing wears through, a seal degrades, a circuit develops a microscopic crack that propagates into thermal cycling until one day, without warning, it gives way entirely. A valve corrodes, a pump loses efficiency. A software system accumulates errors across thousands of operational cycles until its outputs drift imperceptibly from what they were designed to produce. Engineers have a name for this inevitable process. They call it entropy, and in the context of a generation ship drifting through interstellar space for 3 centuries, entropy is not just an inconvenience. It is the slow, patient, unstoppable enemy of every living soul aboard. Let us ground this in something concrete before we scale up to the full terror of it. The most complex machine currently operated continuously by human beings is probably the International Space Station. It has been continuously inhabited since November 2nd, 2000. That is now well over 2 decades of uninterrupted operation. In that time, it has required constant maintenance, dozens of spacewalks performed specifically to repair or replace failing components, regular resupply missions delivering spare parts, replacement hardware, fresh consumables. Entire systems have been upgraded, replaced, or jury-rigged to continue functioning beyond their original design lifetimes. The station's solar arrays, originally designed to last 15 years, are now operating well beyond that window and showing measurable degradation. The station's outer hull has been struck thousands of times by micrometeorites and orbital debris, creating a patchwork of minor damage that requires ongoing monitoring. And the International Space Station sits in low Earth orbit, roughly 400 kilometers above the surface. If something goes catastrophically wrong, a crew can be evacuated and back on the ground within hours. Resupply vehicles arrive multiple times per year. Teams of engineers on Earth monitor every system continuously in real time and can dispatch solutions within days. None of that is available on a generation ship, not even remotely. Now, let us think about what a generation ship actually contains, mechanically and systemically, and what the maintenance demands of that vessel would look like across 3 centuries. Start with propulsion. Whatever drive system the ship uses, whether it is a nuclear pulse drive, a fusion torch, an antimatter engine, or something more exotic, it is operating under conditions of extraordinary stress, at scales we have never built before, for durations we have never attempted. The materials science challenges alone are staggering. Components operating at extreme temperatures, pressures, and radiation levels will degrade faster than components in benign environments. And the propulsion system is not something you can simply switch off and repair at leisure. On a journey with specific velocity requirements and precise trajectory calculations, propulsion anomalies can cascade into navigational disasters. Arrive at Proxima Centauri b, traveling a fraction too fast with insufficient deceleration capacity, and you do not land. You fly past at interstellar velocity into the void beyond, with no way to turn around, no destination ahead, and no way home. Then there is power generation. A vessel supporting tens of thousands of people for 3 centuries requires continuous, reliable power on a massive scale for life support, for food production lighting, for water reclamation, for propulsion, for computing systems, for medical equipment, for heating, for manufacturing. The most credible proposals for generation ship power involve nuclear fission or fusion reactors. Nuclear fission reactors have demonstrated impressive longevity. Some designs can operate for decades with relatively modest maintenance, but decades is not centuries. Reactor components, particularly those exposed to neutron flux, become progressively embrittled over time through a process called neutron irradiation damage. Fuel assemblies require replacement. Coolant systems develop leaks, shielding degrades, and a reactor failure aboard a generation ship is not just a power outage, it is potentially a radiation emergency affecting every person aboard. Beyond propulsion and power, consider the sheer number of individual systems that have to keep working simultaneously without interruption for 300 years. Atmospheric processes that scrub carbon dioxide and maintain oxygen levels. Water reclamation systems cycling thousands of liters per hour through filtration, purification and redistribution. Agricultural systems maintaining precise growing conditions across massive hydroponic or aeroponic installations. Medical facilities equipped to handle surgery, childbirth, epidemic disease, psychiatric emergencies, genetic screening, manufacturing facilities capable of producing replacement parts for every other system aboard, structural monitoring systems tracking the integrity of a hull that will be struck by interstellar dust particles traveling at a significant fraction of the ship's velocity, each impact carrying enormous kinetic energy. Computing infrastructure managing the integration of all these systems simultaneously. Each of these domains contains hundreds, perhaps thousands, of individual components that will eventually fail, and the relationship between these systems is not modular and independent, it is deeply, intricately interconnected. A fault in the atmospheric processing system affects the agricultural system because plants require specific atmospheric compositions. A fault in the power system affects everything simultaneously. A fault in the water reclamation system affects both agriculture and human survival directly. A fault in the computing infrastructure affects the monitoring and management of every other system. When you map the dependency relationships between all the systems of a generation ship, what you see is not a collection of separate machines. What you see is a single, extraordinarily complex organism in which the failure of any sufficiently critical node can propagate through the entire body. Systems engineers have a term for this characteristic: tight coupling. When systems are tightly coupled, failures propagate rapidly and often unpredictably because the components are so interdependent that a problem in one place quickly manifests as problems in places that seem unrelated. The sociologist Charles Perrow wrote a landmark analysis of this phenomenon in 1984 in a book called Normal Accidents, arguing that in sufficiently complex, tightly coupled systems, catastrophic accidents are not aberrations, they are statistical inevitabilities. Given enough time and enough operational cycles, some combination of simultaneous minor failures will cascade into a major one in ways that no designer anticipated and no operator can prevent in real time. He called them normal accidents, not because they are common in any given moment, but because they are the normal expected outcome of operating complex, tightly coupled systems over long enough timescales. A generation ship is perhaps the most complex, most tightly coupled system ever conceived, and it would need to operate without a catastrophic normal accident for 300 years. Now add the human element to the engineering problem, And things get even more complicated. Machines do not maintain themselves. Every inspection, every repair, every replacement of a worn component requires human beings with the knowledge, the tools, and the physical ability to perform the work. We touched on knowledge extinction earlier, but let us look at it more concretely in the engineering context. Modern industrial systems are maintained by specialists who have spent years in dedicated training programs, working under the supervision of experienced practitioners, building the kind of deep tacit knowledge that comes only from direct hands-on experience with specific equipment. A nuclear reactor operator does not learn their craft from a manual. They spend years in simulation environments, in training reactors, in supervised operational roles, before they are trusted to work independently. A materials engineer diagnosing metal fatigue in a structural component brings not just textbook knowledge but pattern recognition developed over a career of seeing what real failure looks like in real materials under real conditions. Across 300 years aboard a generation ship, that kind of expertise has to be continuously regenerated, generation after generation, in every technical domain the ship requires. And the challenge is not just transmitting the knowledge, it is maintaining the motivation to acquire it. Consider a young person born aboard the ship in Generation 8. They are told that they must dedicate years of their life to studying reactor engineering, a complex, demanding field, so that they can maintain a system they will spend their career servicing, but never fully understanding in the way its original designers did, working toward a destination they will never reach, on behalf of a mission whose original meaning has become increasingly abstract to them. Why would they do it? What makes that sacrifice feel meaningful and worthwhile? On Earth, technical careers carry social status, financial reward, and the satisfaction of contributing to a living, changing civilization. On a generation ship, the social and reward structures available are whatever the closed community has developed, which may or may not successfully motivate the specific behaviors the ship's survival requires. There is no guarantee that the values and incentive structures of Generation 8 look anything like those of the founding generation. And yet the ship needs its reactors maintained regardless of what Generation 8 finds meaningful. Some researchers propose solving this through rigid occupational assignment, essentially telling people from birth or early childhood what role they will fill based on the ship's needs rather than individual aptitude or desire. This solves the labor supply problem in the narrowest sense. It creates devastating psychological problems in almost every other sense, because it is a direct assault on the autonomy and self-determination that we just talked about, are fundamental to human psychological health. There is another dimension of the engineering problem that almost never gets discussed in popular accounts of generation ships, but which engineers who work on long-duration space systems regard as one of the most serious challenges of all material availability and manufacturing capability. A generation ship carries a finite amount of every material it will ever have. There is no restocking, no emergency shipment of a particular alloy that turns out to be critically necessary, no ability to order a component that was not anticipated at the time of departure. Every gram of every substance aboard is all you will ever have. This means that the manufacturing systems aboard the ship, the facilities for producing new components, refabricating worn ones, and synthesizing necessary materials must be capable of working with whatever is available in whatever quantities remain to produce whatever is needed for 3 centuries. That requires a manufacturing capability of almost unimaginable versatility and sophistication. You need the ability to smelt and machine metals, fabricate polymers, produce electronic components, synthesize chemical compounds, grow biological materials, and do all of this at the scale and precision required by the most demanding systems aboard the vessel. Modern manufacturing on Earth is a globally distributed system of extraordinary complexity. The components in your smartphone were manufactured in dozens of countries using raw materials sourced from across the planet, processed using specialized equipment built by yet more specialized manufacturers, assembled in facilities whose supply chains involve thousands of separate vendors. No single location on Earth, and certainly no single vessel in space, replicates anything approaching that capability. Three-dimensional printing and advanced fabrication technologies have been proposed as part of the solution, and they are genuinely relevant. But current additive manufacturing, for all its impressive advances, cannot produce every type of component with the material properties and tolerances required by critical systems like reactor components, medical implants, or precision optical equipment. The gap between what we can currently manufacture in a self-contained environment and what a generation ship would need to produce is still enormous. Here is the synthesis of everything we have covered in this section, stated as directly as possible. A generation ship requires the most reliable, most resilient, most self-maintaining complex system ever conceived by human engineering. It must operate without catastrophic failure for 3 centuries. It must be maintained by populations whose knowledge, motivation, and technical capability cannot be guaranteed across generations. It must produce its own replacement components from a finite material budget, and it must do all of this while simultaneously sustaining the biological, ecological, genetic, and psychological health of tens of thousands of human beings in total isolation. No machine we have ever built comes close to meeting those requirements. The longest-running complex human-built systems, ancient aqueducts, cathedral structures, some industrial installations, have survived centuries, but they are passive structures maintained by access to the full resources of human civilization on Earth. Nothing active, nothing life-critical, nothing of comparable complexity has ever operated reliably for 300 years without external support. Does that mean it is impossible? Probably not. Human engineering has achieved things that previous generations considered impossible over and over again. But it does mean that the gap between where we are now and where we would need to be is not a gap of decades. It is a gap of perhaps centuries of engineering development. And it means that anyone who tells you a generation ship is just around the corner is either selling you something or has not looked carefully at the numbers. And yet, and here is the thing that makes this entire conversation so extraordinary, all of these problems stacked on top of each other do not exhaust the challenge. Because even if you solve the radiation problem and crack the ecology problem and manage the genetics perfectly and maintain the psychological health of the population and keep the machines running for 3 centuries, you still have to actually arrive somewhere worth going. And that brings us to a problem so vast it operates on a completely different scale from everything we have discussed so far. Now we are going to look at what we actually know about the destinations, the exoplanets that might theoretically receive a generation ship, and why the universe, in its characteristic fashion, has arranged things to be even more difficult than the distance alone would suggest. Let us imagine for a moment that everything has gone right. 300 years have passed. The ship has held together. The ecology has remained stable. The population has maintained its genetic diversity. The people aboard, descendants of descendants of descendants of the original crew, have somehow preserved both the technical knowledge to keep the vessel running and the psychological coherence to remain a functional society. Against every odd we have spent the last 5 parts examining, they have made it. The destination star grows visibly brighter in the forward observation panels. Deceleration burns have been firing for decades, bleeding off the enormous velocity accumulated over centuries of acceleration. The ship is slowing, the star is resolving from a point of light into a disk, and orbiting it, right there, in the data streaming from the ship's instruments, is the planet they came for. Now the question that nobody in the excited early planning meetings adequately answered becomes suddenly, urgently, terrifyingly real. What if it is not what they were hoping for? This is the destination problem, and it is far more serious, far more scientifically grounded, and far less discussed than almost any other aspect of the generation ship challenge. Because the uncomfortable truth is this: the planets we are most likely to send a generation ship toward are, based on everything current astronomy and planetary science tells us, quite possibly profoundly hostile to human life in ways that no amount of human endurance or engineering ingenuity can simply overcome. Let us start with the most obvious target. Proxima Centauri b, discovered in 2016 by a team of astronomers using the HARPS spectrograph at the European Southern Observatory in Chile. Proxima Centauri b caused an enormous wave of excitement in the scientific community and the broader public. Here was a rocky planet with a mass at least 1.17 times that of Earth, orbiting within the habitable zone of the nearest star to our Sun. The habitable zone, sometimes called the Goldilocks zone, is the range of orbital distances around a star where a planet's surface temperature could theoretically allow liquid water to exist. And liquid water, as far as we currently understand, is the fundamental prerequisite for life as we know it. On the surface, it sounded extraordinary, a potentially Earth-like world orbiting the nearest star, just 4.24 light-years away. If any destination for a generation ship made sense, surely this was it. But the more carefully planetary scientists have looked at Proxima Centauri b, the more the initial excitement has given way to a much more sober and complex picture. And that picture is shaped almost entirely by one factor: the nature of Proxima Centauri itself. Proxima Centauri is a red dwarf star. Red dwarfs are the most common type of star in the Milky Way. They make up somewhere around 70 to 75% of all stars in our galaxy. They are small, cool, and extraordinarily long-lived, burning their nuclear fuel so slowly that some will remain on the main sequence for trillions of years, far longer than the current age of the universe. In many ways, they seem appealing as hosts for habitable worlds, but red dwarfs have a problem. Actually, they have several, and they are serious enough that a significant fraction of the planetary science community now regards planets in the habitable zones of red dwarfs as unlikely candidates for surface habitability, at least by anything resembling Earth life. The first problem is stellar flares. Proxima Centauri is what astronomers call a flare star, meaning it produces stellar flares with a frequency and intensity that dwarfs anything our own Sun generates. A solar flare from our Sun is a significant event, capable of disrupting satellite communications and power grids on Earth. Our planet's magnetic field and thick atmosphere absorb the brunt of the radiation and particle bombardment. But Proxima Centauri produces flares that are, in relative terms, vastly more energetic compared to its baseline luminosity. In 2017, astronomers documented a superflare from Proxima Centauri that was roughly 10 times more energetic than the most powerful solar flare ever recorded from our Sun in terms of its ultraviolet output relative to the star's normal emission. And this was not a rare event. Proxima Centauri produces significant flares multiple times per day. The implications for a planet in its habitable zone are severe. Ultraviolet and X-ray radiation from these flares would bombard the planetary surface with enough intensity to destroy complex organic molecules and sterilize surface environments, unless the planet possesses a thick, protective atmosphere and a strong magnetic field. And here is where the second major problem with Proxima Centauri b emerges. Because Proxima Centauri b almost certainly does not rotate the way Earth does. It orbits its star at a distance of only about 0.05 astronomical units, roughly 1/20th of the distance between Earth and our Sun. At that proximity, gravitational interactions between the planet and its star almost certainly produce a phenomenon called tidal locking. A tidally locked planet rotates exactly once per orbit, meaning one hemisphere permanently faces the star, baking in perpetual daylight, while the other hemisphere faces permanently away, locked in permanent, frozen darkness. Proxima Centauri b's orbital period is approximately 11.2 Earth days. So one side of the planet experiences roughly 11 Earth days of continuous stellar radiation, and the other experiences 11 Earth days of continuous, lightless cold. The atmospheric and climatic consequences of tidal locking are profound and deeply problematic. Atmospheric modeling studies suggest that a tidally locked planet could potentially maintain a habitable zone around its terminator, the twilight boundary between the permanently lit and permanently dark hemispheres. But the atmospheric dynamics required to maintain this are extraordinarily sensitive to initial conditions. A too thin atmosphere freezes out entirely on the dark side, collapses, and the planet loses it altogether. A too thick atmosphere creates runaway greenhouse effects or atmospheric superrotation patterns that redistribute heat in complex and potentially destructive ways. Threading that needle requires a very specific set of planetary characteristics that we currently have no way to confirm Proxima Centauri b actually possesses. And then there is the magnetic field question. Earth's magnetic field, generated by the circulation of its liquid iron outer core in a process called the geodynamo, is essential to our habitability. It deflects the solar wind, protecting our atmosphere from being gradually stripped away by the continuous pressure of charged particles flowing outward from the Sun. Mars lost its global magnetic field billions of years ago, and its atmosphere, once potentially thick enough to support liquid water, has been progressively eroded by the solar wind ever since. Mars today has an atmospheric pressure less than 1% of Earth's at the surface. Whether Proxima Centauri b possesses a magnetic field capable of protecting its atmosphere from the intense stellar wind of its parent star is unknown. The stellar wind from Proxima Centauri is estimated to be roughly 2,000 times more intense at the planet's orbital distance than the solar wind is at Earth's orbit. Even if the planet has a magnetic field, there is a real question about whether it is strong enough to withstand that bombardment across geological timescales, let alone preserve an atmosphere suitable for human beings. Now, you might be thinking, all right, but maybe Proxima Centauri b is not the target. Maybe we aim for a better candidate. And this is where the broader picture of exoplanet science becomes both inspiring and sobering in equal measure. Since the launch of the Kepler Space Telescope in 2009, and subsequently the Transiting Exoplanet Survey satellite, TESS, launched in 2018, our catalogue of known exoplanets has exploded. As of the mid-2020s, we have confirmed more than 5,500 exoplanets, with thousands more candidates awaiting confirmation. Statistical analyses suggest that virtually every star in the Milky Way hosts at least one planet, and that rocky planets in or near habitable zones are genuinely common across the galaxy. That is one of the most profound discoveries in the history of astronomy. The universe is full of worlds, but here is the critical distinction that often gets lost in popular coverage of these discoveries. Being in the habitable zone is a necessary condition for surface habitability, but it is nowhere near a sufficient one. Earth itself sits in our Sun's habitable zone, but so does Venus, a hellscape with a surface temperature of around 465 degrees Celsius. atmospheric pressure 90 times that of Earth, and clouds of sulfuric acid swirling through an atmosphere composed almost entirely of carbon dioxide. Venus is, by every measure, profoundly uninhabitable, and it sits comfortably within our Sun's habitable zone. The James Webb Space Telescope, which began scientific operations in 2022, has given us our first genuine ability to characterize exoplanet atmospheres in meaningful detail. Early results have been extraordinary and instructive. In 2023, Webb observations of the TRAPPIST-1 system, 7 rocky planets orbiting an ultra-cool red dwarf about 40 light-years from Earth, 3 of which sit in the habitable zone, began providing atmospheric constraints on several of the planets. The initial results for TRAPPIST-1c, a rocky planet somewhat similar in size to Venus, suggested it likely lacks a substantial carbon dioxide atmosphere, pointing toward either a thin atmosphere or a bare rocky surface, neither of which is particularly promising for habitability. Results for other planets in the system are still being refined, but the emerging picture is complicated. What Webb is teaching us, one observation at a time, is that characterizing an exoplanet's true habitability, its atmospheric composition, its surface conditions, its geological activity, its water inventory, requires data that we simply do not yet have for any world beyond our own solar system. We can identify candidates, we can constrain possibilities, but we cannot, with current technology, confirm that any specific exoplanet is actually habitable by human beings, or even by any form of life as we understand it. And here is the existential weight of that limitation in the context of a generation ship. You are asking people to commit, not just themselves, but their children and their children's children, for 10 generations, to a journey whose destination you cannot verify in advance. You are asking a civilization to sacrifice everything, to endure centuries of hardship and confinement and loss, to travel across an ocean of darkness so vast it defies imagination, on the basis of incomplete information about whether what waits at the other end is a new home or a dead rock. The probability that any specific nearby exoplanet is immediately habitable by human beings without extraordinary technological intervention is, based on current scientific understanding, quite low. Not zero, but quite low. The conditions required for Earth-like surface habitability are numerous, specific, and apparently somewhat rare even in a universe full of rocky planets. You need the right stellar type, providing stable radiation over geological timescales. You need the right planetary mass, maintaining a geologically active interior with plate tectonics to cycle carbon and regulate atmospheric composition. You need the right distance from the star, in a habitable zone that accounts for the star's evolving luminosity. You need a magnetic field strong enough to protect the atmosphere. You need enough water, delivered perhaps by ancient cometary impacts. You need the right atmospheric composition, produced and maintained by a complex interplay of geological, chemical, and biological processes. Earth has all of these things. We know of no other world, in all the thousands of exoplanets we have confirmed, that we can say with confidence has all of them together. So what does arrival actually look like? If the planet is not immediately habitable, the most commonly proposed answer is terraforming, the deliberate modification of a planet's environment to make it habitable for Earth life. It is a concept that has fired human imagination for over a century, and the theoretical frameworks for how it might work are genuinely interesting. You might seed the atmosphere with greenhouse gases to warm a cold planet. You might introduce photosynthetic organisms to begin producing oxygen. You might deliver volatiles by redirecting comets. Over centuries or millennia, you might gradually push the planet's environment towards something approaching Earth-like conditions. But terraforming, even in the most optimistic projections, takes thousands to tens of thousands of years. The people who arrive on the generation ship after 300 years of travel would not step out onto a verdant, breathing world. They would step out, if they could step out at all, onto something that might, with enormous continued effort across further millennia, eventually become a world their distant descendants could inhabit without technological support. In the meantime, the arrival population would need to continue living inside enclosed, artificial environments, not unlike the ship they just spent 3 centuries aboard, but now stationary on a planetary surface rather than moving through space. They would trade one form of confinement for another. The destination would look, in the day-to-day lived experience of the people who arrived, remarkably similar to the journey. There is something almost poetic about that, in the way that the universe's most humbling truths tend to be poetic. We dream of reaching the stars and finding new worlds waiting for us, ready and welcoming, like pages in a book written for human hands to turn. But the universe did not write that book for us. It did not arrange its planets for our convenience or calibrate its stars for our comfort. The cosmos is not hostile. It is simply, profoundly indifferent. And in that indifference lies one of the deepest invitations to genuine wisdom that the universe has to offer. We are extraordinary creatures, shaped by 4 billion years of biological evolution on a very specific world, fine-tuned by natural selection for the conditions of one particular pale blue dot. We cannot simply step off that dot and onto another without confronting the full weight of what that specificity means. And yet, and this is the thought that should sit with you as we move forward, the fact that it is so difficult is not a reason to abandon the dream. It is a reason to take the dream seriously enough to be honest about it, to understand it clearly, to build toward it with the full rigor and humility that it deserves. Because we are going to turn the conversation in a different direction. We have explored why a generation ship mission would be brutally, perhaps fatally, difficult for the kinds of human beings we currently are. Now we are going to ask the question that changes everything. What if we do not send the humans we currently are? Everything we have explored so far has operated under a single, quietly enormous assumption. It is so fundamental that it has sat beneath every argument, every statistic, every cautionary example we have examined, like bedrock beneath a landscape, and it is this: that the people we send to the stars are people like us, biological human beings, creatures of flesh and bone and electrochemical thought, shaped by millions of years of evolution on a warm, wet, gravity-bound world. People who need food and water and air and sleep and love and meaning and the freedom to make their own choices. People who get lonely and frightened and angry and bored. People who age and die and leave behind children who are subtly, stubbornly different from their parents. That assumption has driven every problem we have identified. The radiation vulnerability comes from having biological tissue. The psychological fragility comes from having evolved minds. The genetic bottleneck comes from sexual reproduction. The mission drift comes from the human hunger for autonomy and self-determination. The engineering entropy problem is, at its core, a problem of depending on biological human beings to maintain machines across timescales that exceed any individual human lifespan by orders of magnitude. So the most radical question in the entire field of interstellar mission planning is simply this: what if we change the assumption? What if the beings who cross the interstellar void are not quite, or not entirely, the kinds of beings who left? Let us start with the gentlest version of this idea, because it sits closest to technologies we are already beginning to develop, and then we will move progressively outward into territory that is simultaneously more technically speculative and more philosophically profound. The gentlest version is suspended animation, hibernation, the idea that you put the crew to sleep in some medically induced state of dramatically reduced biological activity, and wake them up at the other end. If you could genuinely achieve this, it would dissolve most of the problems. No multi-generational population to manage, no mission drift, because the same people who left are the ones who arrive. No psychological deterioration from centuries of confinement, because the subjective experience of the journey is compressed to something approaching zero. No accumulation of radiation damage across generations, because the crew is not actively metabolizing. No knowledge extinction, because the knowledge stays inside the same brains that acquired it. It sounds almost too good. And in the way of things that sound too good, it comes with serious complications. True suspended animation, the kind where you cool a human body down to near-freezing temperatures, halt biological processes almost entirely, and then successfully revive the person without damage, does not currently exist for human beings. What does exist, in a limited clinical context, is therapeutic hypothermia. Doctors sometimes cool patients to around 32 to 34 degrees Celsius to reduce brain damage after cardiac arrest or during certain types of surgery. This is a carefully managed, short-duration intervention, lasting hours at most, with a very specific and narrow medical purpose. Going from therapeutic hypothermia lasting a few hours to genuine suspended animation lasting decades or centuries is not an incremental engineering improvement. It is a qualitative leap into entirely different biological territory. The core problem is ice. When you cool biological tissue, water molecules begin to form ice crystals. Ice crystals are structurally sharp, and they rupture cell membranes with devastating efficiency. The damage caused by ice crystal formation inside cells, a process called cryoinjury, is severe and at sufficiently low temperatures, currently irreversible. This is why cryonics, the practice of freezing recently deceased people in liquid nitrogen at -196 degrees Celsius in the hope of future revival, remains scientifically controversial and, based on current understanding, almost certainly incapable of preserving the structural integrity of the brain's neural connections in ways that would allow meaningful revival. Researchers are working on approaches that might sidestep the ice problem. Cryoprotective agents, chemicals that prevent ice crystal formation by replacing water in cells with substances that vitrify, turning into a glass-like amorphous solid rather than crystalline ice, have shown some promising results in small biological systems. In 2022, researchers published results showing successful cryopreservation and revival of a coral species using cryoprotectant techniques adapted from work on human tissues. Organs have been successfully vitrified and rewarmed in laboratory settings. These are genuine, meaningful advances, but scaling from an organ to a complete human body and from a few hours of preservation to decades involves biological complexity that current science has not yet approached. The brain alone, with its roughly 86 billion neurons and approximately 100 trillion synaptic connections, each one encoding some fragment of a person's memories, personality, and identity, presents a preservation challenge of almost incomprehensible delicacy. There is also the question of what happens biologically over decades of even deeply reduced metabolic activity. Completely stopping all biological processes is not the same as dramatically slowing them. At any temperature above absolute zero, chemical reactions continue, however slowly. Radiation damage accumulates, perhaps more slowly than in an active metabolizing person, but it does not stop. DNA repair mechanisms, which normally work continuously to correct radiation-induced damage, are themselves slowed or halted. Over decades of interstellar travel, the cumulative effect on preserved biological tissue is unknown, and the theoretical arguments are not encouraging. Some researchers have looked at natural analogues for inspiration. Certain species of tardigrades, the microscopic animals sometimes called water bears, can enter a state called cryptobiosis, essentially shutting down their metabolism almost entirely in response to desiccation or extreme cold, and reviving later. Some tardigrades have been revived after decades in a desiccated state. Certain nematode worms and some species of insects demonstrate similar capabilities, but the biological mechanisms that allow these organisms to enter and exit cryptobiosis are deeply integrated into their cellular architecture in ways that have no simple equivalent in mammals. We cannot extract the tardigrade's cryptobiosis capability and transplant it into human cells, at least not with anything approaching current biotechnology. So suspended animation, as a solution to the generation ship problem, remains genuinely promising as a long-term research direction, but it is nowhere near a deployable technology for any mission we could realistically plan in the near future. The gap between where we are and where we would need to be is measured not in engineering refinements, but in fundamental biological breakthroughs that may or may not prove achievable. Moving further out along the spectrum of radical solutions, we encounter something that makes suspended animation look conservative. And that is deliberate human genetic modification, engineering the biology of the mission's participants so that they are genuinely better suited to the challenges of interstellar travel. This idea is not science fiction anymore. The tools of genetic engineering have advanced with breathtaking speed over the past 2 decades. CRISPR-Cas9, the gene editing technology developed primarily through the work of Jennifer Doudna and Emmanuelle Charpentier, who jointly received the Nobel Prize in Chemistry in 2020, allows researchers to make precise, targeted edits to DNA sequences with a specificity and ease that was utterly unimaginable even 15 years earlier. We are now in the early stages of clinical gene therapy trials for conditions ranging from sickle cell disease to certain forms of inherited blindness, with results that are genuinely remarkable. But the kind of genetic modification relevant to a generation ship mission goes far beyond treating single gene disorders. We are talking about engineering human beings with meaningfully enhanced radiation resistance, enhanced psychological resilience to confinement and isolation, reduced caloric requirements, lowering the food production burden on the ship's agricultural systems, perhaps enhanced cognitive capabilities for maintaining complex technical knowledge across generations, perhaps extended lifespans, reducing generational turnover and preserving institutional knowledge longer within individual minds. Each of these modifications is, in principle, a direction that genetic science might eventually move toward. Some organisms already possess genetic adaptations relevant to these challenges. The bacterium Deinococcus radiodurans, sometimes called Conan the bacterium by researchers who study it, possesses extraordinary radiation resistance through a suite of highly efficient DNA repair mechanisms that allow it to survive radiation doses thousands of times higher than those that would kill a human being. Understanding and potentially adapting those mechanisms for human cells is a serious area of research. But here is where the science collides with something far more complex than engineering. Modifying human beings, particularly the germline modifications that would be inherited by all subsequent generations, raises ethical, philosophical, and social questions of staggering depth. Who decides what modifications are made? Who decides what traits constitute improvements? Who has the authority to alter the genetic inheritance of people who have not yet been born and cannot consent to their own modification? These are not abstract philosophical puzzles. They are live, urgent, contested questions in the bioethics community right now, and the world's major scientific and regulatory bodies are actively grappling with them. In 2018, a Chinese scientist named He Jiankui shocked the global scientific community by announcing that he had edited the genomes of human embryos, resulting in the birth of twin girls with CRISPR-edited CCR5 genes intended to confer resistance to HIV infection. The scientific community's response was immediate and overwhelmingly negative. He was condemned by researchers worldwide, imprisoned by Chinese authorities, and the incident is now widely cited as a cautionary example of the ethical abyss that opens up when genetic modification of human beings is pursued without appropriate oversight, transparency, or societal consent. The scientific consensus is clear. Germline editing of human embryos for enhancement purposes, as opposed to treating severe disease, is not ethically acceptable under current norms and understanding. A generation ship program that proposed to genetically engineer its population would be entering this territory and would need to resolve questions that human civilization has not yet come anywhere near answering. What does it mean to be human if we deliberately redesign ourselves? If the people who arrive at Proxima Centauri b after 300 years are genetically distinct from the people who left Earth, not through the gradual process of natural evolution, but through deliberate design, are they still human in any meaningful sense? Does it matter? These are not rhetorical questions. They are genuine ones, and the answers are not obvious. Further still along the spectrum, we encounter proposals that leave the biological entirely behind, or at least that leave biology behind as the primary substrate for human identity and experience. The concept of uploading human consciousness, digitizing the neural patterns of a mind in sufficient detail to run them as software on a computing substrate, has been discussed seriously by researchers and philosophers for decades. If it were achievable, it would arguably dissolve every biological problem associated with interstellar travel simultaneously. Digital minds do not need food or water or air. They are immune to radiation in the conventional biological sense. They do not age. They do not suffer from inbreeding depression. They can be copied, backed up, paused, and resumed. The subjective experience of a 300-year journey could be compressed into an arbitrary duration by adjusting the speed of computation. But consciousness uploading faces what philosophers call the hard problem of consciousness in its most acute form. We do not fully understand what consciousness is. We do not know whether a sufficiently accurate computational model of a brain would give rise to genuine subjective experience, the feeling of what it is like to be someone, or whether it would be an extraordinarily sophisticated simulation of the outward behavior of a conscious being, hollow at its core. This is not a problem that more computing power or better scanning technology automatically resolves. It is a deep conceptual and philosophical problem about the nature of mind and experience that remains genuinely unresolved despite decades of serious inquiry. Even setting the philosophical questions aside, the technical requirements for consciousness uploading are far beyond anything we can currently envision. Scanning a human brain at the resolution required to capture its functional connectivity, not just the coarse structure of its regions, but the specific weights and properties of its individual synaptic connections, would require imaging capabilities that do not exist and that current physics suggests would require destructive sampling of the tissue being scanned. You might, in theory, be able to create a digital model of a brain. Whether that model would be you or merely a copy that believes itself to be you while the original ceases to exist is a question that may not have a clean answer. There is one more radical proposal worth examining, and it is in some ways the most psychologically interesting of all. It is called the seed ship concept. Rather than sending fully grown human beings or people in suspended animation or digitized minds, a seed ship would carry frozen human embryos or even just genetic material, eggs, sperm, and the genomic data needed to reconstruct human diversity alongside artificial intelligence systems sophisticated enough to gestate, birth, and raise the first generation of humans at the destination. This approach sidesteps most of the biological problems entirely. Frozen embryos require minimal resources and space compared to living people. The journey is made by machines, not biological beings, eliminating the life support, ecological and psychological challenges of the multi-generational scenario. At the destination, the AI systems would incubate and raise the first humans, teaching them language, culture, science, and everything else needed to begin building a civilization on the new world. The technical challenges of this approach are still enormous. Maintaining frozen embryos in viable condition across centuries in the radiation environment of deep space requires solving essentially the same biological preservation problems we discussed in the context of suspended animation. Building artificial intelligence systems capable of successfully raising human children, not just technically competent but psychologically healthy, emotionally secure, socially functional human beings, requires a level of AI sophistication and reliability that far exceeds anything we currently possess or can clearly envision. But the deeper challenge of the seed ship concept is one that cuts right to the heart of what we actually mean when we talk about sending humanity to the stars. The children raised by AI systems at a distant star would be genetically human, but would they be human in the full sense? They would have no connection to Earth's history, to the accumulated wisdom of human civilization, to the living culture of the species that created them, except what the AI systems chose to transmit. Their entire understanding of what it means to be human would be mediated through artificial minds designed by people who lived and died centuries earlier. Is that humanity? Is that a civilization? Or is it something new? Something that began as human but arrived as something else? Here is the thread that runs through every single one of these radical proposals, from suspended animation to genetic engineering to digital minds to seed ships. Every one of them requires us to answer, before we can meaningfully evaluate the technology, a prior question that is not technological at all. What are we actually trying to preserve when we talk about sending humanity to the stars? If the answer is biological human DNA, the genetic sequence of our species, then a seed ship probably makes sense as the most efficient vehicle for that goal. If the answer is human consciousness and experience, the subjective inner lives of specific people, then suspended animation, if it ever becomes possible, is the most faithful approach. If the answer is human culture, knowledge, and civilizational continuity, the accumulated story of what we have learned and made and become, then the multi-generational ship, for all its problems, is arguably the most honest attempt because it sends whole living societies rather than biological raw material or frozen minds. And if the answer is simply the capacity to ask questions, to look up at an alien sky and feel wonder, to reach out across the darkness and try to understand, then perhaps any vessel that carries that capacity, in whatever form it takes, is carrying humanity in the only sense that ultimately matters. That question, what are we actually trying to send to the stars, is one that science alone cannot answer. It reaches into philosophy, into ethics, into the deepest questions about human identity and value and purpose. And it is a question that, if we are being honest with ourselves, we need to answer before we can meaningfully design the mission, because the mission is not really about reaching a planet. It has never been about reaching a planet. It is about deciding what we believe humanity is, and then finding the courage to carry that belief across the void. There is a thought experiment that physicists and engineers who work seriously on interstellar travel sometimes use to frame the entire problem. It goes like this. Imagine you are standing at the edge of an ocean. You need to reach an island on the other side. The ocean is so wide that no human being has ever crossed it. You have two choices. You can build a ship large enough and stocked well enough to carry not just you, but your children and your grandchildren and every generation after them, for however long the crossing takes. A floating civilization, self-contained and self-sustaining, committed to the journey for centuries. Or you can wait for a faster boat, one that could make the crossing in a single lifetime, or a single year, or a single day. The generation ship in this analogy is the first option. It does not require better propulsion. It does not require a technological breakthrough. It requires only what we already understand, the physics of momentum and mass and fuel, scaled up to an almost incomprehensible degree. It is, in a very real sense, the brute force solution to interstellar travel. And the question that haunts every serious discussion of it is whether the brute force solution is worth pursuing at all, given that faster alternatives might be achievable within a time frame that makes the generation ship obsolete before the first one ever leaves dry dock. So let us do what this channel always tries to do. Let us look at what the physics and the engineering actually say, not what science fiction imagines, not what optimistic startup pitch decks promise. What the hard numbers and the peer-reviewed science currently suggest. Start with where we are right now. The fastest human-made object ever launched is the Parker Solar Probe, which, as of its closest solar approaches, has reached speeds of around 690,000 kilometers per hour, roughly 0.064% of the speed of light. That is genuinely extraordinary by any historical measure. It is also, in interstellar terms, essentially stationary. At that speed, a journey to Proxima Centauri would take approximately 6,700 years. The Voyager 1 spacecraft, our most distant human-made object, travels at around 61,000 kilometers per hour, roughly 0.006% of the speed of light. At that pace, as we noted earlier, the journey to Proxima Centauri takes around 73,000 years. These numbers establish the baseline, the gap between our current maximum velocity and the velocities required for interstellar travel within a human lifetime, or even within a few centuries, is not a gap of 10 or 20%. It is a gap of multiple orders of magnitude. To reach Proxima Centauri in 100 years, you need to travel at roughly 4.2% of the speed of light. To get there in 25 years, within a human working lifetime, you need to reach approximately 17% of the speed of light. To get there in a single year, you need to be traveling at a substantial fraction of the speed of light, approaching 80 or 90%. How do you get there? Let us go through the most seriously proposed concepts in roughly ascending order of ambition and departing from current technical reality. The first serious concept is nuclear pulse propulsion. The basic idea is elegant in its brutal simplicity. You detonate a series of nuclear explosions behind the spacecraft and ride the pressure wave of each detonation forward. The concept was formalized in the late 1950s and early 1960s under a program called Project Orion, led in part by the physicist Freeman Dyson at the General Atomics Corporation. Dyson's calculations suggested that a large enough Orion-class vehicle could achieve velocities of roughly 3 to 5% of the speed of light using fission bombs, and potentially higher with thermonuclear, hydrogen bomb detonations. Project Orion was cancelled in 1963, largely due to the Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space, but the physics has never been seriously challenged. Nuclear pulse propulsion could in principle work. A modified version of the concept, Project Daedalus, studied by the British Interplanetary Society in the 1970s, proposed using inertial confinement fusion micro-explosions rather than fission bombs, and calculated that a robotic probe could reach Barnard's star, roughly 5.9 light-years away, in about 50 years, achieving around 12% of the speed of light. The engineering challenges are formidable. You need to produce, store, and reliably detonate fusion fuel pellets at a rate of roughly 250 per second for the acceleration phase of the mission. The pusher plate, the enormous dish structure at the rear of the spacecraft that absorbs the pulse of each explosion and transfers its momentum to the ship, must withstand repeated extreme mechanical and thermal shocks over years of continuous operation. The structural requirements are at the very edge of materials science. But there is no new physics involved. Nuclear pulse propulsion operates entirely within well-understood physical principles, and if the engineering could be realized, it would represent a genuine pathway to interstellar travel on timescales of decades rather than centuries. For a crewed mission, the velocity achievable with realistic fusion pulse designs sits in the range of roughly 10 to 15% of the speed of light, giving journey times to Proxima Centauri in the range of 30 to 40 years. That is still more than a human career. You would leave as a young adult and arrive in old age if you were still alive, but it is within a single generation. No generational succession required. The same people who left would arrive, or at least some of them would, moving further out. We reach laser sail propulsion, and specifically the concept that has attracted the most serious scientific and financial attention of any interstellar proposal in recent decades. Breakthrough Starshot, announced in 2016 by the Breakthrough Initiatives organization, with backing from figures including the late Stephen Hawking, the Russian billionaire Yuri Milner, and Facebook co-founder Mark Zuckerberg. Breakthrough Starshot proposes sending a fleet of gram-scale spacecraft, essentially postage stamp-sized chips carrying miniaturized instruments, to Proxima Centauri and the Alpha Centauri system, using powerful ground-based laser arrays to accelerate them. The concept works like this. An array of ground-based lasers, collectively producing on the order of 100 gigawatts of power, focuses its combined beam on an ultra-thin, highly reflective sail attached to the tiny spacecraft. The radiation pressure of the laser beam, the physical force exerted by photons striking the reflective surface, accelerates the spacecraft. The proposed target velocity is 20% of the speed of light, which would give a journey time of roughly 20 years to Alpha Centauri. At that velocity, the spacecraft would fly through the Alpha Centauri system, take measurements and images, and transmit the data back to Earth, where it would arrive 4.2 years later. The physics of Breakthrough Starshot are sound. Laser propulsion is not a speculative concept. Small laser sail demonstrations have already been performed in Earth orbit. The principle scales. The engineering, however, presents challenges that its proponents openly acknowledge are formidable. 100 gigawatts of coherent, precisely aimed laser power does not exist. For comparison, the total electrical generating capacity of the United Kingdom is roughly 70 to 80 gigawatts. Focusing a beam of that power on a target the size of a postage stamp over distances that grow from thousands of kilometers to millions of kilometers during the acceleration phase, while maintaining precise alignment to within a tiny fraction of an arc-second, requires laser and adaptive optics technology far beyond anything currently deployed. The sail material must be extraordinarily thin, measured in nanometers, yet reflective enough to withstand the incredible intensity of the focused beam without ablating or tearing. At the target velocity of 20% the speed of light, interstellar dust grains become high-energy projectiles capable of vaporizing the sail or the instrument package on impact. Perhaps most significantly, Breakthrough Starshot as currently conceived would send robotic probes, not human beings. Scaling the concept to carry a crewed vessel, even a very small one, changes the mass budget by many orders of magnitude, and the laser power requirements scale directly with the mass to be accelerated. A crude Starshot-class vessel would require laser arrays so powerful they would present serious concerns about atmospheric heating and other planetary-scale effects. Breakthrough Starshot is genuinely exciting as a pathway to robotic, interstellar exploration within this century. As a pathway to crewed interstellar travel, it requires technological leaps that have not yet been seriously mapped out. Now we reach the territory where the engineering begins to shade into the speculative, though the physics remains legitimate. Fusion drives, spacecraft propelled by controlled nuclear fusion reactions, using the fusion exhaust as propellant, represent perhaps the most credible pathway to practical crewed interstellar travel if they can be realized. Unlike nuclear pulse propulsion, which relies on discrete explosions, a fusion drive would ideally produce a continuous, sustained exhaust of fusion products, helium nuclei and high-energy neutrons, providing steady thrust over months or years. The fundamental advantage of fusion over chemical or even fission propulsion is specific impulse, the efficiency with which propellant mass is converted into thrust. Fusion reactions release roughly 10 million times more energy per kilogram of fuel than chemical combustion. This means a fusion-powered spacecraft could achieve the same velocity change with enormously less propellant mass than a chemical rocket, making the mission mass budget far more manageable. The catch, of course, is that we have not yet achieved sustained net energy positive fusion in any terrestrial facility. As of the mid-2020s, fusion energy research has achieved genuinely historic milestones. In December 2022, the National Ignition Facility at Lawrence Livermore National Laboratory in California reported achieving fusion ignition for the first time, a target compression that released more fusion energy than the laser energy delivered to it. This was a landmark moment rightly celebrated, but the laser energy required to drive the ignition was itself a tiny fraction of the total electrical energy consumed by the facility to produce and fire the lasers. Net energy gain in any practically meaningful sense remains a future achievement. The ITER project, the International Thermonuclear Experimental Reactor, being built in southern France through an unprecedented international collaboration involving 35 nations, aims to demonstrate net plasma energy gain of a factor of 10 by the early 2030s. ITER is a tokamak design using powerful magnetic fields to confine the superheated plasma. If it achieves its goals, it will be a transformative moment in energy physics. But ITER is a research facility, not a prototype power plant. The distance from ITER's scientific demonstration to a fusion engine compact and powerful enough to propel a spacecraft remains very large. Private fusion companies, Commonwealth Fusion Systems, TAE Technologies, Helion Energy, and others are pursuing faster timelines to practical fusion than the traditional big science approach, and some have made genuinely impressive technical progress. The field is moving faster than it was a decade ago. But even the most optimistic, credible projections for practical fusion power on Earth are measured in decades. Scaling that to spacecraft propulsion adds further decades of development. The earliest plausible timeline for a fusion-powered crewed interstellar mission, under anything approaching realistic assumptions, sits well into the 22nd century. Further out still, we reach antimatter propulsion, the concept that generates the highest specific impulse of any known physics-based propulsion system. When matter and antimatter meet, they annihilate each other completely, converting 100% of their rest mass into energy, primarily in the form of high-energy gamma rays and pions. The energy yield per kilogram is roughly 10 billion times that of chemical combustion and roughly 1,000 times that of fusion. In principle, an antimatter drive could achieve a significant fraction of the speed of light with a fuel mass that is merely a fraction of the total spacecraft mass. resolving the tyranny of the rocket equation that hamstrings every other propulsion concept. The problem with antimatter is not the physics. The physics is unimpeachable. The problem is production and storage. Antimatter does not exist in useful quantities anywhere in the accessible universe, at least not in forms we can collect or harvest. It must be manufactured in particle accelerators, one particle at a time, by slamming beams of high-energy protons into targets and collecting the antiprotons produced in the collisions. The process is extraordinarily inefficient. CERN's Antiproton Decelerator Facility, the world's primary antimatter production facility, produces on the order of a few nanograms of antiprotons per year, at an energy cost roughly 10 billion times greater than the energy content of the antimatter produced. To fuel a crewed interstellar mission, you would need on the order of hundreds of tons of antimatter, produced and stored at a cost and energy expenditure that is, under any currently imaginable technology, completely prohibitive. George presents its own challenge. Antimatter annihilates on contact with normal matter, which means it must be stored in magnetic confinement traps, penning traps that suspend the antiparticles in a vacuum, isolated from all contact with the trap walls. Current technology can store only tiny quantities of antiprotons for limited periods. Scaling to the quantities required for propulsion, with storage times of years, represents a technological challenge of a completely different order. Antimatter propulsion remains, at present, a legitimate long-term aspiration rather than an engineering program. It requires breakthroughs in particle physics, materials science, and energy production that have no clear near-term pathway. So here is the honest synthesis of everything the physics and the engineering currently tell us. There is no propulsion technology available today or clearly achievable within the next few decades that would make crewed interstellar travel fast enough to eliminate the generational succession problem entirely. Nuclear pulse propulsion is the closest thing to a near-term buildable option, but even it delivers journey times measured in decades, long enough that the crew would age significantly during the crossing, and that careful mission design around crew longevity would be required. Laser sail concepts like breakthrough Starshot are exciting for robotic probes, but face enormous scaling challenges for crewed missions. Fusion drives are genuinely promising, but require a breakthrough in controlled fusion that has not yet been achieved. Antimatter remains a theoretical aspiration. The generation ship is not the option we choose because it is fast or elegant. It is the option we might be forced into if we decide that reaching other stars before the 23rd or 24th century is a priority worth pursuing, and we cannot wait for the better boats. But here is what makes this entire conversation so much more than a technical feasibility study. The generation ship is not ultimately about propulsion or ecology or radiation shielding or population genetics. It is about something far deeper. It is about what drives human beings to point themselves at the darkness and push forward anyway, even knowing what the crossing costs. And now we are going to talk about why that impulse, however irrational it might seem from a strictly cost-benefit perspective, may be the most important thing about us. We are going to talk about what the history of human exploration actually tells us, what it means that we are the only species, as far as we know, in the entire history of this 4.5 billion-year-old planet that has looked at the night sky and felt called by it. What the generation ship represents, not as an engineering project, but as a statement about the kind of creature we are and the kind of future we dare to imagine. 70,000 years ago, give or take a few thousand, a small group of anatomically modern human beings did something that no member of our species had ever done before. They crossed water, not a river, not a shallow estuary, open ocean. They built or found some kind of watercraft, looked out at a horizon beyond which there was nothing visible, nothing known, no guarantee of anything at all, and they went anyway. They crossed from what is now Southeast Asia to the landmass of Australia, covering stretches of open sea that, even at the lowest sea levels of that glacial period, required deliberate, sustained navigation across dozens of kilometers of open water. We do not know their names. We do not know what they called themselves, what language they spoke, what they believed about the ocean, or the sky, or their place in the world. We know they existed because their descendants are still there, the Aboriginal Australians, whose civilization represents the longest unbroken cultural continuity in human history, stretching back to that original crossing across a horizon that no human eye had ever seen before. Think about what that crossing required. Not the technology was primitive by any subsequent standard. What it required was something far more extraordinary and far more specifically human. It required the capacity to imagine a destination that could not be seen, to conceive of a world beyond the known world, to weigh the terror of the unknown against the pull of curiosity and the pressure of necessity, and to choose forward that capacity, that specific, strange, almost irrational willingness to cross the horizon is not incidental to what we are. It is not a quirk or an accident. It is one of the deepest and most consistent expressions of human nature across the entire span of our existence as a species. And understanding it, really understanding it, changes everything about how you think about the generation ship. Consider the full sweep of human expansion across this planet. Roughly 65,000 years ago, the ancestors of all non-African people alive today began leaving Africa, the continent where our species originated and where we had lived for the previous 200,000 years or so. They crossed into the Levant, spread across Asia, reached Europe, crossed land bridges into the Americas during periods of lower sea levels, and eventually reached virtually every habitable corner of the Earth's surface, every ecosystem, every climate zone, Arctic tundra, equatorial rainforest, high-altitude plateau, arid desert. They reached the islands of the Pacific, the most remote landmasses on the surface of the planet, scattered across the largest ocean in the world, through deliberate, sophisticated open ocean navigation, using stars and waves and wind patterns and the flight paths of birds as instruments of guidance. Centuries before European seafarers even imagined the Pacific existed, the Polynesian expansion across the Pacific, which unfolded between roughly 3,000 and 1,000 years ago, is one of the most extraordinary achievements in all of human history. At its furthest reach, Polynesian navigators reached Easter Island, Rapa Nui, a tiny volcanic speck roughly 3,500 kilometers from the nearest inhabited land, and roughly 3,700 kilometers from the coast of South America. They reached Hawaii, nearly 4,000 kilometers from the nearest previous Polynesian settlement. They reached New Zealand, Aotearoa, bringing with them not just people but an entire cultural and biological package: plants, animals, tools, knowledge systems, genealogies, cosmologies. They did this without metal tools, without written charts, without compasses, without GPS, without any communication with the world they had left behind. They did this in double-hulled canoes across open ocean, carrying families and communities, committing entirely to the crossing with no guarantee of what waited on the other side. Sound familiar? The parallels between Polynesian ocean navigation and the generation ship concept are not superficial, they are structural. In both cases, you have a vessel carrying a community, not just individuals but a society, across a medium hostile to human life, toward a destination beyond visual range, without the possibility of turning back once the crossing is fully committed. In both cases, the journey takes long enough that the social fabric of the voyaging community must be maintained for its duration. In both cases, Success depends not just on the technology of the vessel, but on the navigational knowledge, the social cohesion, and the collective will of the people aboard. The Polynesian navigators did not wait for better boats before they crossed the Pacific. They crossed it with the boats they had because the pull of the horizon was stronger than the weight of the risk. And they succeeded, not always, not in every attempt, but overwhelmingly enough that within a few centuries their descendants occupied every habitable island across the largest ocean on Earth. Now here is the perspective shift that I want you to sit with, because it reframes every single problem we examined, every challenge we have described: the radiation, the ecology, the genetics, the psychology, the engineering entropy, the uncertain destination. These are real, they are serious. They represent genuine barriers between where humanity is now and a successful interstellar civilization. Nothing in this video has exaggerated them or invented them. The science behind every single one of them is solid and current. And yet, the people who first crossed into Australia faced challenges that were, by the standards of their time and their technology, every bit as formidable. They had no weather forecasting, no structural engineering, no understanding of ocean currents in any formalized scientific sense, no way to know what waited on the other side, or even for certain that anything waited at all. The mortality rate on those first crossings was almost certainly significant. Some attempts probably failed entirely. People drowned, canoes were lost, communities were scattered. They crossed anyway. And every human being alive today who has any ancestry outside of Africa exists because of the accumulated effect of that crossing and thousands like it. The relentless, sometimes catastrophic, ultimately triumphant human habit of going anyway. What changed between those first ocean crossings and today is not the fundamental human impulse. What changed is the scale of the challenge and, critically, the scale of our capability to address it. The gap between our current technology and what a generation ship requires is real and vast, but it is not a gap of a different kind from the gaps our ancestors bridged. It is a gap of the same kind, inflated to a cosmic scale. There is something else worth considering about the deep history of human exploration that rarely enters the generation ship conversation. And it is this: the most important thing our ancestors carried across every horizon was not their tools or their food, or even their genetic material. It was their stories. Every human culture that has ever existed has organized itself around narrative, around explanations of where we came from, what we are, why we are here, and where we are going. These stories are not decorations on the surface of human civilization. They are its structural skeleton. They are what holds a community together across time, across hardship, across the deaths of individuals and the forgetting of specifics. They are what transmits values from one generation to the next in forms vivid and compelling enough to actually shape behavior. The Aboriginal Australians who crossed the sea 70,000 years ago carried cosmologies, explanatory frameworks for the universe that were sophisticated enough to encode detailed geographical and astronomical knowledge in forms that have survived across tens of thousands of years. The dreaming, the complex system of narratives, lore, and cosmology at the heart of Aboriginal culture contains within it navigational information about water sources, dangerous terrain, and seasonal resources, encoded in songlines that traverse the continent. This is oral tradition doing what written records do in literate cultures, but with a resilience and a depth of time that written records have never approached. What stories would a generation ship carry? What cosmologies would sustain people across 3 centuries in the dark? What narratives would be compelling enough to hold a community together, to motivate the maintenance of critical systems, to carry the mission's purpose through generation after generation of people who never chose it and never knew anything else? This is not a trivial question. It may be the most important design question of the entire mission, because as we discussed before, the generation ship's greatest vulnerability is not mechanical or biological. It is motivational and meaning-related. It is the fragility of the human need to feel that what you are doing matters, that your sacrifice is not absurd, that your life inside a metal tube between the stars is not a diminishment, but a contribution to something genuinely, cosmically significant. And here is the extraordinary thing. The story that could do that work is not one we need to invent. It is one that the science itself tells us, if we listen to it carefully enough. You are made of atoms forged in the cores of stars that lived and died before our sun existed. The iron in your blood was produced in the heart of a massive star that exploded as a supernova roughly 4.5 billion years ago, seeding the cloud of gas and dust that eventually collapsed to form our solar system. The carbon in your DNA, the oxygen in every breath you take, the calcium in your bones, all of it was synthesized in stellar interiors and distributed across the galaxy by the violence of stellar death. You are not on this planet. You are not separate from the cosmos, observing it from outside. You are the cosmos in one of its most extraordinary local arrangements, looking at itself. The physicist Carl Sagan said it with characteristic precision. We are a way for the cosmos to know itself, and he was not speaking metaphorically. He was making a literally accurate statement about what happens when matter organizes itself into the complexity of a human nervous system. The universe, through us, has developed the capacity for self-reflection, for curiosity, for the specific kind of love that looks up at the night sky and feels called home by it. A generation ship mission viewed from this perspective is not a desperate escape from a failing planet, or a colonial project, or an engineering challenge, or even a survival strategy. It is the universe continuing its own exploration of itself through the medium of the only beings in the known cosmos who have ever looked at the stars and said, "We want to go there." Every generation aboard that ship, whether they chose the mission or were born into it, would be participating in something that has been building since the first hydrogen atoms clumped together under gravity 13.8 billion years ago. They would be a chapter in a story whose first sentence was the Big Bang, and whose last sentence, if there is one, has not been written yet and may never be. That is not a small story. That is the largest story there is, and it is true. Now let us zoom back to the present, because there is something important about where we actually are in this story. This moment, right now, in the history of our species, that deserves to be said clearly. We are, as far as we currently know, the only beings in the observable universe who are having this conversation. We are the only species in the 4.5 billion year history of life on Earth that has looked at the stars and developed the mathematics to understand what they are. We are the only creatures who have built machines capable of leaving the gravity well of their home planet, of traveling to another world and setting foot on it, of sending probes to the edge of interstellar space and listening to the data they transmit back across the void. We did all of that in roughly a century of serious technological development. 1 century out of 4.5 billion years. We went from the first controlled powered flight at Kitty Hawk in 1903 to landing human beings on the moon in 1969, 66 years. We went from Sputnik in 1957 to a spacecraft crossing the heliopause into interstellar space in 2012, 55 years. The arc of what we are capable of, measured against the timescale of the cosmos, is essentially vertical. We are just beginning. We are at the very first moments of what a spacefaring civilization might eventually become, and we are already asking questions that reach across 4 light-years and 400 trillion kilometers. The generation ship in this context is not a sign of limitation. It is a sign of extraordinary ambition. It is what you attempt when you are a young, impatient species that has decided it will not wait for perfection before beginning. It is what you do when the call of the horizon is stronger than the weight of the obstacles, and the obstacles are real, every single one of them. The science is honest about that, and so is this channel, always. The radiation will be brutal, the ecology will be fragile, the psychology will be tested in ways we have never tested it. The machines will try to fail, the destination may disappoint, the people who arrive may be different, in ways deep and unpredictable from the people who left. But here is the thing about human beings and horizons. We have always been different on the other side from what we were when we started. Every crossing changes the people who make it. The Polynesians who reached Hawaii were not the same as the people who had left the Society Islands a few generations earlier. Their language had shifted, their cosmology had adapted to new stars. Their culture had evolved in response to new challenges and new landscapes. They were still human, they were still Polynesian, but they were also something new, something that could only have come into existence by making the crossing. The people who arrive at Proxima Centauri b, if they ever do, in whatever form, through whatever means, across whatever span of time, will be different from us. They will be shaped by the crossing in ways we cannot predict and perhaps cannot imagine. Their understanding of what it means to be human will have been forged in a context so profoundly alien to our own experience that their answers to the deepest questions may surprise and perhaps humble us. And that act of becoming something new in response to the demands of a new horizon may be the most essentially, irreducibly human thing of all. If you are still watching, make sure to subscribe to the channel. Your support makes all the difference to this community. The radiation and the ecology and the genetics and the psychology and the engineering and the physics and the philosophy. We are going to look at what the honest, current scientific consensus actually says about whether this is achievable and on what time scale. We are going to talk about what is actually being done right now, the research programs, the technology development efforts, the serious scientific initiatives that are laying the groundwork for interstellar exploration, and we are going to end where all honest conversations about the cosmos should end, not with certainty but with the right questions, held open with curiosity and humility and the specific kind of wonder that is the finest thing our species has ever produced. We have traveled a long way together in this video, further, in some respects, than the distance between here and Proxima Centauri, because the distance between here and Proxima Centauri is just space, just emptiness measured in trillions of kilometers, and what we have actually been traveling through is something far more complex and far more interesting than empty space. We have been traveling through the full dimensionality of what it would mean to be human. In transit, between the stars, we have looked at the radiation that would silently work on biological tissue for centuries. We have looked at the closed ecological systems that have never in human history been maintained without external intervention for any period approaching what an interstellar journey requires. We have looked at the population genetics mathematics that demands tens of thousands of people just to preserve biological health across 300 years. We have looked at the psychology of confinement and mission drift and the fundamental human need for autonomy and meaning. We have looked at the engineering entropy problem, the relentless, patient tendency of every machine ever built to eventually fail. We have looked at the destination itself, at the troubled, flare-bombarded surface of Proxima Centauri b, and at what current planetary science honestly says about the likelihood of finding a welcoming world at the end of the crossing. We have looked at the radical alternatives, suspended animation, genetic engineering, digital mines, seed ships, and what each of them requires us to decide about what we are actually trying to preserve when we talk about sending humanity to the stars. We have looked at the propulsion physics, from nuclear pulse drives to laser sails to fusion engines to antimatter, and what the honest engineering assessment says about timelines and feasibility. And we have looked at the deep human history of exploration, at the crossings our ancestors made across oceans they could not see the far side of, and what those crossings tell us about the specific, extraordinary, almost irrational thing that drives our species toward every horizon it encounters. Now it is time to ask the question that all of that has been building toward. What does the honest scientific verdict actually say? Where do we actually stand? And what, if anything, is being done right now that might change the picture? The honest verdict, stated as clearly and as fairly as the current science allows, is this: a generation ship mission to Proxima Centauri or any other nearby star system is not impossible. The word impossible is one that science uses carefully and rarely, and it does not apply here. There is nothing in the known laws of physics that absolutely forbids a self-contained vessel carrying a human population across interstellar distances over multiple centuries. The obstacles we have described are not the obstacles of physics. They are the obstacles of engineering and biology and psychology and social organization, which is to say, they are the obstacles of insufficient knowledge and insufficient capability. And insufficient knowledge and insufficient capability are the specific kinds of obstacles that human beings are historically very good at overcoming, given enough time and enough motivation. But the honest verdict also says this: we are not ready, not by a modest margin, not by a generation of engineering development. We are not ready by a gap that is measured in the most optimistic, realistic assessment, in centuries of scientific and technological progress. Every single one of the problems we have described, every single one remains at present either unsolved or solved only in principle, with no buildable, testable, deployable solution currently in hand. The radiation problem has no complete engineering solution. The closed ecology problem has no demonstrated long-duration solution at any relevant scale. The population genetics problem has a theoretical numerical answer, but no governance or social framework for implementing it. The psychology and mission drift problem has no solution that has ever been tested across anything approaching the relevant timescales. The engineering entropy problem has no precedent for management across centuries of isolated operation. The destination uncertainty problem has no resolution available until we can characterize exoplanet atmospheres and surfaces in far greater detail than current or near-future telescopes permit. Taken together, these are not small gaps. They are civilizational-scale challenges, each one of which could occupy generations of the world's best scientists and engineers before yielding a workable answer. And yet, and here is the part that should make you feel not despair, but something closer to the opposite, the work has begun. Quietly, seriously, in laboratories and research centers and university departments around the world, human beings are already building the foundations of the knowledge that a generation ship mission would eventually require. Let us look at what is actually happening. In the field of radiation biology, researchers at NASA's Space Radiation Laboratory at Brookhaven National Laboratory in New York have been conducting systematic studies of the biological effects of galactic cosmic ray exposure on living organisms for years. Using particle accelerators to simulate the high-energy heavy ions characteristic of GCR radiation, they have been mapping the dose-response relationships for cancer risk, central nervous system effects, and cardiovascular damage in animal models. This research is directly informing the design of radiation protection standards for future deep space missions, including the Artemis program's planned crewed lunar surface missions and eventual Mars missions. Every piece of data generated is a building block toward understanding, and eventually mitigating one of the generation ship's most lethal challenges in closed-loop life support. The advanced closed-loop system developed by the European Space Agency and tested aboard the International Space Station has demonstrated the ability to regenerate oxygen from carbon dioxide by combining it with hydrogen, a significant step toward greater atmospheric closure. NASA's work on bioregenerative life support, using plant growth chambers to simultaneously produce food and recycle air and water, has been ongoing for decades through programs like the Controlled Ecological Life Support System, or CELS. Researchers at the University of Arizona, among others, have been developing compact, highly efficient closed-loop agricultural systems that minimize water and nutrient loss while maximizing caloric output per unit of mass and volume. None of these systems are yet at the scale or closure fraction a generation ship requires. But the research direction is clear and the progress is real. In population genetics, the work of researchers like Cameron Smith has been extended and refined by colleagues working at the intersection of genomics and space medicine. There is serious, peer-reviewed scientific literature on the minimum viable population question, on the genetic management protocols that might be required for multi-century isolated communities, and on the genomic diversity metrics that a founding population would need to meet. This body of knowledge is still young and still developing, but it exists, which means the problem is at least being asked in the right scientific language. In Psychology and Human Factors, the lessons from Mars analog missions, the NASA Human Exploration Research Analog Facility in Houston, the HICS Habitat in Hawaii, the Mars 500 simulation conducted in Moscow between 2010 and 2011, in which 6 volunteers spent 520 days in a sealed facility simulating a Mars mission, are being systematically studied and codified. The Mars 500 study in particular produced a rich body of data on crew psychology, sleep disruption, motivation, and interpersonal dynamics over extended isolated confinement. Researchers at institutions including the International Space University and the NASA Johnson Space Center are using this data to develop better crew selection criteria, better conflict resolution protocols, and better mission design principles for long-duration isolated missions. In propulsion physics, the work on laser sail technology is progressing through Breakthrough Starshot's research program, with small-scale demonstrations of sail materials and laser sail dynamics already published in peer-reviewed journals. Research on compact fusion systems, particularly the high-temperature superconducting magnet technology being developed by Commonwealth Fusion Systems, which achieved a world record magnetic field strength in its demonstration magnets in 2021, is advancing toward the Spark Fusion demonstration experiment expected to operate in the mid-2020s. If compact fusion is achieved, the downstream implications for spacecraft propulsion will be among the most significant technology developments of the century. And in planetary science, the James Webb Space Telescope is systematically building our understanding of exoplanet atmospheres in ways that no previous instrument could achieve. Every new spectrum of a transiting exoplanet's atmosphere is another data point in the map of what is actually out there. What kinds of worlds are common? What atmospheric compositions occur naturally around which types of stars, where the conditions for habitability might genuinely exist? Webb is not the last word. The proposed next-generation space telescopes, concepts like the Habitable Worlds Observatory, a space-based telescope designed specifically to image and characterize potentially habitable exoplanets in reflected starlight, would push this characterization capability dramatically further. If funded and built, such an observatory could, within a few decades, give us genuine, detailed atmospheric and surface data on the nearest potentially habitable exoplanets, including potentially answering the question of whether any of them show signs of biological activity. So the picture that emerges from looking honestly at where the science currently stands is not one of impossibility. It is one of immaturity, of a species in the early stages of developing the knowledge it would need to attempt something of this magnitude responsibly. It is the picture of a civilization that has identified, with remarkable precision and intellectual honesty, exactly how hard the problem is, and that is already in dozens of separate research streams simultaneously beginning the work of solving it. That is actually extraordinary. Step back and appreciate what that means. We are, right now in the 2020s, a species that has been in space for less than 70 years, that first set foot on another world just over 50 years ago, that has sent exactly one spacecraft beyond the boundaries of our own solar system. And we are already doing the science, building the knowledge, running the experiments that might, centuries from now, make it possible for our descendants to cross 4 light years of darkness in a vessel carrying an entire civilization. We are laying the foundations of a cathedral that we will never see completed, and there is something profoundly, deeply human about that. The builders of the great medieval cathedrals of Europe, Notre Dame de Paris, begun in 1163 and not completed for nearly 2 centuries. Cologne Cathedral, whose construction began in 1248 and was not finished until 1880, knew that they would never live to see the spires rise. They built anyway. They cut the stone, laid the foundations, raised the first courses of wall, knowing that the completion of the work was a gift they were giving not to themselves, but to people who had not yet been born. We are doing the same thing. Every radiation biology experiment at Brookhaven, every closed-loop ecology trial, every fusion magnet test, every exoplanet atmosphere spectrum from the James Webb Space Telescope, these are stones being cut for a cathedral whose completion lies beyond our own lifetimes, and the people who will one day stand inside it, looking up at the vault of an alien sky through the transparent panels of a generation ship or a colony dome on a distant world, will be the inheritors of work that began here in this century with this generation. There is one more thing I want to say before we close, and it is perhaps the most important thing in this entire video. It is something that gets lost in the technical weeds of radiation shielding and population genetics and propulsion physics, but that lies at the heart of why any of this matters. The generation ship is hard because we are extraordinary. Every single problem we have described in this video, every biological vulnerability, every psychological complexity, every social fragility, every depth of need for meaning and autonomy and connection, is a problem precisely because human beings are not simple. We are not machines, and we are not animals acting purely on instinct. We are conscious, questioning, meaning-making creatures with inner lives of staggering richness and depth. We feel loneliness and wonder and love and grief. We build philosophies and compose music and write poetry about our place in the cosmos. We are restless in ways that mere survival does not explain. We need more than food and air. We need purpose. We need beauty. We need the horizon. The generation ship is hard because sending creatures as complex and as magnificent as human beings across 4 light years of darkness is genuinely cosmically hard. It would be far easier to send bacteria, far easier to send machines. The reason we want to send people, the reason the generation ship dream persists despite everything, is that we understand, somewhere beneath the engineering calculations and the population genetics models and the propulsion physics, that a universe explored only by machines has not really been explored at all. Not in the way that matters, not in the way that produces the specific, irreplaceable thing that happens when a conscious mind encounters something vast and unknown and is changed by the encounter. We want to send people because people are the point, and that means every obstacle we face is not evidence that the dream is wrong. It is evidence that the dream is worthy of exactly the difficulty it presents. Easy dreams do not change civilizations, they do not reach across generations, they do not call forth the best of what a species can become. The dreams that matter are the ones that ask more of you than you currently have, and then wait with infinite patience while you grow into the asking. Look up tonight if you can. Find a dark enough patch of sky away from the city lights and look for the constellation Centaurus, visible from the southern hemisphere and from lower latitudes of the northern. Inside that constellation, invisible to the naked eye but locatable with a modest telescope, is Proxima Centauri, a dim, faintly red point of light, the nearest star to our Sun, 4.24 light-years away, 40 trillion kilometers, a distance so vast that the fastest spacecraft we have ever built would take 73,000 years to cross it. And orbiting that dim red star, 11.2 Earth days per orbit, roughly 0.05 astronomical units from its surface, is a rocky planet that may or may not have an atmosphere, that may or may not have liquid water, that may or may not be capable of supporting any form of life as we understand it. A planet about which we currently know almost nothing that matters, and everything that is essential. It is there. It is real. It is 4.24 light-years away, and somewhere in the deep future of our species, in centuries or millennia we will never live to see. Shaped by scientific and technological and cultural developments we cannot predict or imagine, something that began as human will cross that distance. It will be extraordinary in ways we cannot foresee. It will carry something of us forward into a darkness so deep that the light of our sun will be just one more faint star among millions. It will look back, perhaps, at the pale blue point of Earth's reflected sunlight and feel something, some complex, irreducible thing that is the distant descendant of what you feel right now, looking up at the sky and wondering. We are stardust wondering about stars. We are the universe reaching for itself across the dark. That is not a small story. That is the whole story, and it is still being written. And if this video left you genuinely curious about what crossing interstellar distances actually takes, start with 1 light-year, just one. Click the video on your screen right now to see how long it would really take us to travel 1 light-year, because the answer will completely change how you think about everything we just talked about.